What if there's a lot more to the universe than we currently understand? Imagine we're only scratching the surface of a much bigger mystery. Think about the beginning of everything, the cosmos, and all the stuff in it that's hard to detect, like dark matter and dark energy. Science helps us uncover bits of the truth, but there's still so much we don't know. Join us as we delve into the most mind-blowing mysteries in the universe. The story of the universe's beginning is a fascinating journey into the depths of time, where scientific theories spark imagination and curiosity. At the forefront of this exploration is the Big Bang theory, which posits that the universe began as an incredibly hot and dense point approximately 14 billion years ago. In an event of unimaginable energy and expansion, it suddenly erupted, causing space itself to stretch. This expansion continues today, leading to the vast, intricate cosmos we observe. Before the Big Bang, traditional concepts of time and space become murky. Some scientists propose the idea that the universe could have existed in a state of singularity, where the normal laws of physics break down. This mysterious beginning, where everything was confined to a tiny, infinitely dense point, raises important questions about what might have preceded it. Another prominent perspective is the multiverse theory. This theory suggests that our universe could be just one of many, existing alongside an infinite number of other universes, each with its own unique properties and perhaps even different physical laws. If this concept is correct, it reshapes our understanding of reality and suggests that the universe is far richer than we can see. Additionally, some scientists explore cyclical models, which propose that the universe undergoes a series of expansions and contractions, continuously recycling itself in an eternal loop. In such a scenario, what we perceive as the beginning could just be one phase in an endless cycle of birth, death, and rebirth. These theories interact and compete with each other, each offering answers to fundamental questions while also leaving many mysteries unsolved. As we look to the cosmos, we uncover not just our universe's origins, but also invite deeper inquiries into existence itself. Cosmic inflation presents a revolutionary perspective on the beginning of the universe, reshaping how we comprehend its origins. Traditionally, the Big Bang theory proposed that the universe began as a hot, dense point that expanded over time. However, inflation suggests that during its earliest moments, the universe experienced a remarkable period of rapid expansion, much faster than the speed of light. Imagine a balloon that is blown up in an instant. It transforms from a tiny speck into a vast expanse. This swift expansion solves several puzzles associated with the early universe. Without inflation, scientists struggle to explain why different regions of the cosmos appear so uniform and similar, despite being separated by vast distances. Inflation theorizes that once the universe inflated, these regions were once in close proximity, allowing them to equalize in temperature and density before drifting apart. Additionally, inflation provides insight into the large-scale structures we observe today, such as galaxies and clusters. The tiny fluctuations in density caused by quantum effects during the inflationary epoch acted like seeds, growing over time into the vast cosmic web we see now. This concept of fluctuations intertwines with the idea that the universe's structure emerged from randomness, highlighting a deeper connection between the minute and the cosmic. While cosmic inflation refines our understanding, it also introduces complexity. It suggests that many universes could exist, each with different properties, a concept known as the multiverse. This idea challenges the singularity of our universe and raises philosophical questions about what constitutes reality and our place within it. Cosmic inflation not only provides answers to long-standing questions, but also opens the door to new inquiries, transforming how we think about the universe's beginning and the vast, mysterious fabric of existence itself. The Big Bang theory marks the beginning of our universe, a moment when everything we know emerged from an incredibly hot, dense state. Despite its established prominence in cosmology, significant mysteries surround this monumental event and its early moments. To start, the exact condition of the universe at the very moment of the Big Bang remains largely enigmatic. Scientists believe that the universe began expanding rapidly, but the precise mechanics of how everything evolved during those first instants, when temperature and density were unimaginably high, are still poorly understood. This period encompasses what is known as cosmic inflation, a theory suggesting a swift expansion that occurred mere moments after the initial event. However, the details of this process and what may have triggered it remain hypothetical, leaving many questions unanswered. Another profound mystery lies within the formation of the fundamental forces and particles. In those early moments, the universe was a chaotic soup of energy, and as it cooled, particles began to form, transitioning from energy to matter. The unification of the forces, gravity, electromagnetism, and the strong and weak nuclear forces during this time is a topic of intense study. We lack a complete understanding of how these forces developed their distinct characteristics and roles in shaping the universe we inhabit now. Moreover, the period following the Big Bang, known as the radiation era, is somewhat obscured in our current theories. The rapid expansion led to cooling, which allowed protons and neutrons to combine into light elements like hydrogen and helium. However, the exact processes that governed this nucleosynthesis are still being explored. The abundance of these elements hints at a finely tuned balance of conditions present during that era, but our grasp of this phenomenon is still developing. Dark matter and dark energy introduce additional layers of complexity to the narrative of the universe's early history. We know that most of the universe is comprised of these elusive substances, which do not interact with light and thus remain invisible. Their presence is inferred from gravitational effects, but their roles and origins remain a puzzle that haunts cosmologists. Finally, the cosmic microwave background radiation, an afterglow of the Big Bang, offers a glimpse into the universe's infancy. This faint radiation is a relic from when the universe became transparent to light. Studying it has revealed crucial information, yet it continues to unveil mysteries about the initial conditions of the cosmos and the uniformity seen throughout the universe today. In conclusion, while the Big Bang theory provides a fascinating framework for understanding the universe's origins, it is far from complete. Each aspect, from cosmic inflation and the formation of fundamental forces to the nature of dark matter and the remnants of the cosmic microwave background, poses intriguing questions that challenge our knowledge and inspire ongoing research in the field of cosmology. The universe, despite its chaotic beginnings, exhibits a remarkable uniformity that can leave many pondering how such order emerged from what seemed like a tumultuous explosion. Scientists explain this phenomenon through a theory known as cosmic inflation. Imagine the universe as a balloon that, in its infancy, underwent a rapid expansion. In this early stage, the universe expanded faster than the speed of light, smoothing out irregularities and making the distribution of matter and energy more uniform. This swift expansion meant that any initial variations in temperature and density caused by quantum fluctuations in the very early moments were stretched and flattened across vast distances. As the universe continued to expand, these tiny imperfections remained, but they became statistical fluctuations rather than dramatic differences. Furthermore, as matter began to clump together under the influence of gravity, it organized into the structures we observe today, like galaxies and clusters of galaxies. Over billions of years, while local environments may appear chaotic on a grand scale, the universe shows patterns and structures that reflect this initial state of smoothness. Also, the laws of physics, particularly thermodynamics and gravity, play essential roles in establishing this uniformity. Gravity tends to pull matter together, while thermodynamics dictates how energy disperses. Together, they foster a balance that supports the orderly distribution of galaxies across the cosmos. The universe's uniformity is a glimpse into its peaceful aftermath, smoothed by rapid expansion and shaped by fundamental forces, turning chaos into the harmonious cosmos we observe today. Before the Big Bang, the nature of existence as we understand it is shrouded in mystery. Most scientific theories suggest that time and space were not yet formed in any recognizable way. Imagine a state of absolute nothingness, where traditional concepts like time, distance, and matter simply did not apply. This scenario can be difficult to envision since our experience is entirely rooted in a universe filled with these elements. The importance of understanding the conditions before the Big Bang lies in the fundamental questions of existence and the very fabric of reality itself. Scientists delve into this topic to uncover how the universe transitioned from an unfathomable primeval state into the cosmos we observe today. The very idea that something emerged from nothing challenges our understanding of cause and effect. pushing the boundaries of physics and philosophy. Research into this early period often leads to discussions of quantum mechanics and the fundamental forces of nature. For instance, theories propose that fluctuations in a field, often called a quantum field, could have set the stage for the Big Bang to occur, suggesting that tiny, almost imperceptible changes might have sparked the explosive expansion that followed. Moreover, exploring the pre-Big Bang conditions helps to bridge connections with concepts such as black holes and the potential existence of multiple universes. These insights not only enhance our understanding of our cosmos, but also stir curiosity about other realms of existence, possibly altering our perception of reality itself. By investigating what exists before the beginnings of our universe, we approach profound questions about the nature of time, existence, and everything in between, fueling humanity's everlasting quest for knowledge. Dark matter is one of the universe's greatest mysteries. It is a substance that does not emit, absorb, or reflect light, making it completely invisible to our telescopes and senses. Despite its elusive nature, scientists have strong evidence suggesting that dark matter constitutes a significant portion of the universe's total matter. Imagine the universe as a massive cosmic tapestry, where the visible stars and galaxies are like highlights in a broader fabric that remains unseen. This hidden material is thought to exert gravitational forces, influencing the motion of galaxies and clusters of galaxies. The puzzling aspect of dark matter arises from its inability to interact with electromagnetic forces, which means it does not interact with light or any form of radiation in a way that we can directly observe. While we can see how galaxies rotate and how galaxy clusters move within larger structures, the amount of visible matter alone does not account for these movements. Instead, astronomers have inferred the presence of dark matter based on gravitational effects. It's like watching a dance performance where the dancers seem to move in synchrony, while an unseen force is keeping them in line. Scientists have attempted to detect dark matter through various methods, including underground experiments designed to catch rare interactions with ordinary matter and observations of cosmic phenomena. Yet it remains stubbornly out of reach, largely because the known particles that we typically study do not account for it. This uncertainty fuels ongoing research and theorizing, where scientists explore candidates for dark matter particles which may only interact through gravity. Each breakthrough brings new insights, but the question of its composition and exact nature continues to elude our understanding, keeping dark matter as one of the most fascinating enigmas in modern astrophysics. Dark matter plays a crucial role in shaping the universe, particularly in the formation and structure of galaxies. Imagine a traditional scale. The visible matter in galaxies, which includes stars, gas, and dust, is only a fraction of what actually exists. Dark matter, which does not emit light or energy, acts like an invisible frame holding everything together. As galaxies form, they draw in surrounding mass through gravitational attraction. The presence of dark matter creates a gravitational field that exercises a strong influence on visible matter, pulling it toward the centers of galaxies. This is essential because visible matter alone would not have enough gravitational pull to bind galaxies effectively, leading them to be less stable and prone to disintegration or dispersal. The distribution of dark matter within and around galaxies is often shaped like a halo, extending far beyond the visible parts. This dark matter halo influences how galaxies rotate. To visualize this, think of a carousel. While the outer horses should be moving slowly because they are farther from the center, they actually spin at similar speeds to those near the center. This unexpected behavior implies that there is much more mass present than what we can see, and that mass must be due to dark matter. Moreover, dark matter plays a pivotal role in galaxy collisions and interactions. When two galaxies meet, the gravitational tug-of-war is influenced significantly by the surrounding dark matter. Its overwhelming presence helps channel and guide the merger process, impacting the resultant structure and evolution of the new galaxy that emerges. Without dark matter, the universe would look entirely different. It provides the structural backbone that allows galaxies to form, grow, and evolve, acting as a silent but powerful force that shapes the very fabric of cosmic architecture. Dark energy is often referred to as one of the greatest mysteries in modern cosmology due to its elusive nature and the profound implications it has on our understanding of the universe. Imagine our universe as a vast, ever-expanding landscape. While we can see galaxies moving away from us, indicating that space itself is stretching, the reason for this acceleration is tied to dark energy. This enigmatic force is thought to make up a significant portion of the universe's total energy content, much more than both normal matter and dark matter combined. However, scientists have been unable to directly observe dark energy or comprehend its fundamental properties. It behaves in a way that is counterintuitive to our understanding of gravity and matter. Instead of pulling objects together, dark energy seems to push them apart, driving the accelerated rate of expansion. One of the biggest challenges is that, unlike ordinary matter or radiation, dark energy does not interact through any of the known forces. That's why it remains so undetectable. Its effects are felt on cosmic scales over vast distances and immense timescales, which makes experiments and observations incredibly complex. Theories attempting to explain dark energy range from the possibility that it is a property of space itself to ideas involving modifications to our understanding of gravity. Each theory offers a different glimpse into the nature of the universe, but none have yet provided a definitive answer. Consequently, grappling with dark energy not only challenges the foundations of physics, but also invites questions about the ultimate fate of our universe. Will it continue to expand forever, or is there a limit to this growth? The search for answers continues, making dark energy a profound and captivating subject of cosmological inquiry. Detecting and studying dark matter, that mysterious substance thought to make up a significant portion of the universe, is one of the biggest challenges in modern astrophysics. Scientists believe dark matter does not emit light and can only be observed through its gravitational effects on visible matter. To uncover its secrets, researchers are employing several innovative approaches. One way scientists look for dark matter is through large underground detectors. These facilities are designed to catch rare interactions between dark matter particles and ordinary matter. Imagine an incredibly sensitive watch that records the faintest of movements. These detectors use materials that can produce small flashes of light or tiny electrical signals when a dark matter particle collides with an atomic nucleus. The hope is that, although these interactions are extremely rare, they can eventually be captured and understood. Another method involves observing galaxies and galaxy clusters. The influence of dark matter becomes evident in the way galaxies move. If we consider a group of stars moving around a galaxy, their speeds reveal that there must be more mass present than we can account for with visible matter alone. By studying the motion of these celestial bodies, scientists can infer the distribution of dark matter within those galaxies. Furthermore, scientists are also exploring the possibility of creating dark matter particles in high-energy particle collisions. Large particle accelerators like those at CERN smash particles together at incredible speeds, allowing researchers to probe the fundamental building blocks of matter. In this controlled environment, some hope to produce dark matter particles, providing direct evidence of its existence. Finally, astrophysicists observe the cosmic microwave background radiation, an ancient afterglow from the Big Bang. By examining fluctuations in this radiation, scientists can gain insights into how dark matter influenced the formation of structures in the early universe. This method helps paint a broader picture of the cosmos and how dark matter fits into its grand design. As researchers strive to unravel the mysteries of dark matter, these various methods contribute to a multifaceted approach in what promises to be a groundbreaking quest in our understanding of the universe. Each discovery brings scientists one step closer to revealing the elusive nature of this invisible substance that shapes our reality. Dark energy represents one of the most intriguing mysteries in modern astrophysics. Traditionally, gravity, as described by Newton and later refined by Einstein, is a force that attracts objects towards one another. In the framework of our universe, it was expected that this attractive force would result in a slowing down of the expansion of the cosmos over time due to gravitational pull. However, observations suggest otherwise. Data indicates that the universe is not only expanding, but is accelerating in that process. This unexpected behavior introduces the concept of dark energy, a force that seems to counteract the effects of gravity on a grand scale. Imagine blowing up a balloon. As you blow air into it, the balloon expands, reflecting how the universe is stretching out. If gravity were solely at play, we might expect the air inside to pull the sides inward, slowing the expansion. Instead, dark energy acts like an unseen hand pushing the balloon outward even faster. The challenge lies in understanding what dark energy actually is. It makes up a significant portion of the universe's total energy content, yet it interacts with matter in a way that is still unclear. Einstein introduced the cosmological constant a century ago as a way to explain a static universe, but discarded it once it was revealed the universe is expanding. Now, it appears that maintaining a cosmological constant might be closer to the truth. This constant represents a steady energy density filling space, pushing everything apart in a uniform manner. As scientists delve deeper into this conundrum, they confront profound implications for the nature of gravity itself and the fundamental structure of the universe. The existence of dark energy suggests that our understanding of gravity and its role in cosmic evolution is not complete. It challenges us to rethink how forces interact on both macroscopic and microscopic levels, pushing the frontier of physics into areas of theoretical speculation, particularly regarding the very fabric of space and time. The quest to unravel dark energy could very well lead to a new chapter in our grasp of the cosmos. The formation of black holes is shrouded in several intriguing mysteries that captivate scientists and enthusiasts alike. To understand how black holes come into existence, we first need to explore the life cycle of massive stars. When these stars exhaust their nuclear fuel, they can't counterbalance the immense force of gravity pulling inward. This often leads to a dramatic collapse, but the specifics of this process still raise questions. One major mystery revolves around what determines whether a star becomes a black hole or a neutron star after this collapse. Neutron stars represent a different state of matter, often formed when a similar massive star undergoes a supernova explosion, yet retains enough pressure to prevent further collapse. The fine line that separates these outcomes is not fully understood. Scientists are exploring what factors such as mass and rotation impact which path a star follows at the end of its life. Another significant enigma involves the role of stellar mergers in black hole formation. In environments where stars orbit closely together, they can collide and merge, potentially creating black holes. The intricacies of how these mergers occur and the details of the resulting black holes, including their sizes and spins, remain poorly defined. Understanding these interactions could unlock secrets about black holes that we have yet to uncover. Furthermore, the presence of supermassive black holes at the centers of galaxies poses additional questions. These colossal entities are millions to billions of times more massive than our Sun. The mechanisms that would allow such enormous black holes to form in the early universe are still the subject of investigation. Did they grow gradually through merging smaller black holes and absorbing material, or is there a different pathway through which they acquired their immense mass early on in the universe's history? Lastly, the relationship between black holes and dark matter, an unseen substance that influences cosmic structure, remains a profound mystery. Is there a connection between the elusive dark matter and black holes? Unraveling these questions may lead us toward new understandings of the universe and its fundamental components. Each of these mysteries not only enhances our understanding of black holes, but also illuminates the broader nature of the cosmos. Black holes are among the most fascinating objects in the universe, primarily because of their extraordinary ability to warp both space and time. To grasp this concept, envision space as a flexible sheet. When an object with mass, like a planet or a star, sits on this sheet, it creates a dip. The greater the mass, the deeper the dip. Now, when a black hole forms, usually from the collapse of a massive star, it creates an extreme and profound dip in this space-time fabric. This is not merely a small crease, it's like a deep well that profoundly alters the way in which objects move and how time flows around it. As something approaches a black hole, it experiences incredible gravitational forces. This is where the warping of time comes into play. Imagine watching a clock near a black hole. For an observer who is far away, that clock appears to tick more slowly as it gets closer to the black hole. This slowing of time is due to the intense warping of both space and time caused by the black hole's gravity, a phenomenon predicted by Albert Einstein's theory of relativity. The stronger the gravitational pull, the more dramatic this effect becomes. Thus, while someone might feel time passing normally as they near the black hole, An outside observer would perceive it as stretching out. The significance of this warping becomes evident when considering the nature of the universe itself. Understanding how black holes influence time and space aids scientists in grappling with fundamental questions about reality, the fabric of the universe, and the function of gravity. It influences theories on the life cycles of stars, the formation of galaxies, and even the potential for time travel. As researchers continue to study black holes, the insights gleaned shed light on some of the most profound mysteries in science, revealing just how interconnected everything in the cosmos truly is. The mysteries of black holes continue to captivate scientists and astrophysicists alike. At their core, black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. As we delve deeper into understanding what occurs inside these enigmatic giants, various theories emerge, pushing the boundaries of physics. One prevailing idea suggests that when matter crosses the boundary of a black hole, known as the event horizon, it enters a realm governed by extreme gravity. Within this enigmatic territory, classical physics, as we know it, starts to break down. Some theorists propose that matter gets crushed into an infinitely dense point at the center, referred to as a singularity, where the laws of physics as we understand them cease to apply. However, this notion raises questions. If a singularity exists, how does it interact with the universe outside? This is where concepts like quantum mechanics come into play. Some scientists theorize that quantum effects might prevent the formation of a singularity altogether. Instead of collapsing into a single point, matter might create a new state of existence, contributing to a bridge to another universe, or perhaps leading to a process called information preservation, where information about the infalling matter isn't lost, but rather imprinted on the surface of the black hole, known as the event horizon. Another exciting idea is related to the concept of space-time itself. According to some models, the inside of a black hole could be a region of warped space-time, where time behaves differently than in our familiar universe. Some suggest that traveling through a black hole might even lead to other dimensions or parallel universes, opening the door to possibilities that were once purely science fiction. Moreover, researchers are exploring the hints provided by gravitational waves, ripples in space-time created by massive events, such as black hole mergers. These observations may help reveal more about the fundamental structure and behaviors inside a black hole, shedding light on their enigmatic nature. As our understanding evolves, so too do our theories, weaving a complex tapestry of notions that intertwine gravity, quantum mechanics, and the very fabric of reality. The ultimate truth may still be beyond our grasp, but every new discovery brings us a step closer to understanding the true nature of black holes and their intriguing secrets. Black holes represent one of the universe's most intriguing mysteries, particularly in how they intersect with the principles of quantum mechanics. The foundation of this connection lies in the nature of black holes themselves. When a star collapses under its own gravity, it forms a black hole, creating a region of space where gravity is so intense that not even light can escape. This seems to lead to a contradiction when considering what happens to information, which is critical in quantum mechanics. The information paradox arises from the idea that anything falling into a black hole appears to be lost forever. According to quantum mechanics, however, information cannot simply vanish, it must be conserved. This contradiction creates a persistent puzzle in physics. If black holes can swallow up information, where does that information go, and how does it reconcile with the laws of quantum theory? Scientists have proposed various theories to unravel this paradox. One intriguing concept is the idea of black hole evaporation, introduced by the physicist Stephen Hawking. He theorized that black holes can emit radiation, now known as Hawking radiation, causing them to gradually lose mass and eventually disappear. If this process occurs, it poses the question: does the information get lost forever when the black hole evaporates, or is somehow preserved and released as the black hole shrinks? Several physicists propose that the information might be encoded at the black hole's event horizon, the boundary beyond which nothing can escape. This idea suggests that everything that falls into a black hole leaves a sort of imprint at the edge, potentially allowing for the recovery of information over time. These theories delve deeply into the fabric of space-time, suggesting that our understanding of gravity, time, and information is limited, and that further investigations could change how we comprehend the universe. As research in both astrophysics and quantum mechanics continues, the interaction between black holes and the principles of quantum theory remains a dynamic field of study, holding the potential to inform us about the fundamental structure of reality itself. Black holes play a crucial role in the evolution of galaxies, acting as both engines of growth and sources of destruction within galactic environments. At the heart of many galaxies lies a supermassive black hole, which can be millions to billions of times heavier than our Sun. These black holes influence their galaxies in several significant ways. First, as matter spirals inward toward a black hole, it forms an accretion disk, heating up and radiating energy. This process can release immense amounts of energy, impacting star formation in the surrounding regions. In fact, the energy output from these disks can either stimulate the creation of new stars or, conversely, suppress star formation by blowing away gas and dust that would otherwise coalesce into stars. This balancing act between star formation and energy output is vital in determining the structure and future of a galaxy. Additionally, the gravitational pull of supermassive black holes affects the orbits of stars and gas in their vicinity. This intense gravitational environment can lead to complex interactions, including the merging of smaller galaxies into larger ones. As galaxies collide, their central black holes may come together, eventually forming even larger black holes. The merging of galaxies, complemented by this process, plays a significant role in the growth of galaxies over cosmic time. Moreover, black holes influence galactic dynamics through powerful jets. When black holes consume material, they can eject it at near-light speeds in the form of jets that shoot out into space. These jets can impact surrounding gas clouds, further influencing star formation and the overall evolution of the galaxy's structure and star population. Black holes are not merely dormant cosmic monsters, they are active participants in the cosmic ballet of galactic evolution, shaping the interactions and growth of galaxies, impacting star formation, and driving the complex dynamics of our universe. Neutron stars are truly remarkable because they represent one of the universe's most extreme states of matter. Formed when massive stars exhaust their nuclear fuel and collapse under their own gravity, these celestial objects are incredibly dense. Picture compressing the mass of a sun into a sphere roughly the size of a city. This extraordinary density means that a single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. What sets neutron stars apart even further is their composition. They are primarily made up of neutrons, which are subatomic particles that, alongside protons, form the nucleus of atoms. In a neutron star, the gravitational forces are so intense that electrons combine with protons to form neutrons, creating a unique state of matter known as neutronium. This extremely dense material gives neutron stars their incredible gravitational pull. Additionally, many neutron stars are observed as pulsars, which are rapidly spinning stars that emit beams of radiation. As they rotate, these beams sweep across space like lighthouse beacons. The remarkable speed of their rotation can reach hundreds of times per second, generating immense electromagnetic fields. This pulsating behavior allows astronomers to study their properties in great detail, offering insights into fundamental physics and the fabric of the universe. Neutron stars also serve as natural laboratories for studying the interactions of matter under extreme conditions. Their existence challenges our understanding of physics, particularly in fields like quantum mechanics and general relativity. Thus, neutron stars not only showcase the incredible diversity of celestial bodies, but also push the boundaries of our knowledge about the universe itself. Magnetars, a type of neutron star, possess incredibly strong magnetic fields, about 1,000 times stronger than those of ordinary neutron stars. To understand these cosmic oddities, scientists employ a combination of observational techniques and theoretical models. Astronomers often look to the electromagnetic spectrum, especially in the X-ray and gamma-ray ranges, to study magnetars. These regions of light can penetrate dense materials and provide insights into the magnetar's energetic emissions. By observing bursts of radiation that magnetars emit, scientists can infer details about their magnetic fields. For instance, the energy and frequency of these emissions offer clues about the strength of the magnetic field and its effects on the surrounding matter. Additionally, scientists utilize telescopes equipped with advanced detectors to capture these fleeting bursts. Telescopes on Earth and in space, combined with powerful observational techniques, allow researchers to track these events in real time. Different observations are cross-referenced to build a comprehensive understanding of a magnetar's magnetic activity and its effects on the environment around it. The magnetic fields also impact how these stars spin. By studying the rotation rate and any changes in it, researchers gain further insights into the internal structure of the magnetar. Through a combination of direct observation and mathematical modeling, scientists can piece together the mysteries of these extraordinary objects, even without being able to travel to them directly. By integrating data from multiple sources and refining their theoretical frameworks, scientists continue to unravel the profound effects that magnetars have on their surroundings and the fundamental physics at play in the universe. Pulsars are among the most intriguing cosmic objects, offering valuable insights into the life cycle of stars. These highly magnetized, rotating neutron stars emit beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep through space, much like a lighthouse directs its beam to sea. If Earth happens to lie in the path of this beam, we observe a series of regular pulses, which can be incredibly precise, sometimes ticking like a clock. The formation of a pulsar begins with a massive star that has exhausted its nuclear fuel. When this occurs, it can no longer support itself against gravitational collapse. The core implodes, leading to a supernova explosion that blasts the outer layers away. What remains is an incredibly dense core, so dense that a sugar cube-sized amount of pulsar material would weigh as much as all humans combined. This transformed remnant spins rapidly due to conservation of angular momentum, and its intense magnetic field creates the pulsar effect. Studying pulsars gives scientists clues about the conditions prevailing in these extreme environments. The speed at which they spin can tell us about their mass and the processes occurring during their formation. Furthermore, the regularity of their pulses can reveal information about the surrounding environment, such as the presence of nearby matter, which can affect the timing and characteristics of the emissions. Interestingly, pulsars can also be used as cosmic laboratories to test theories of gravity, including general relativity. The precise nature of their timing allows researchers to explore how strong gravitational fields influence light and time. Every mystery these pulsars unveil not only enhances our understanding of stellar evolution, but also deepens our grasp of the fundamental workings of the universe itself. Thus, pulsars are not merely remnants of dead stars. They are key to deciphering the life and death of stars across the cosmos. Neutron stars are among the most fascinating and extreme objects in the universe. They form from the remnants of massive stars that have exhausted their nuclear fuel and undergone a supernova explosion. What remains is a core that has collapsed under its own gravity, compressing matter to an extraordinary degree. This collapse leads to a state where protons and electrons combine to form neutrons, giving rise to an object so dense that just a sugar cube-sized amount of neutron star material would weigh more than an entire mountain on Earth. This extreme density challenges our understanding of matter in several ways. For one, neutron stars are primarily composed of neutrons, which are the building blocks of atomic nuclei. Under normal conditions, such as those found on our planet, matter is governed by the electromagnetic force which keeps atoms and molecules stable. However, in a neutron star, gravity becomes the dominant force, overpowering electromagnetism. This leads to unusual states of matter that we cannot replicate in laboratories on Earth. Furthermore, the very structure of neutron stars raises questions about the nature of nuclear physics. The behavior of neutrons in such extreme environments is not fully understood. Some theories suggest that at their cores, neutron stars might contain exotic forms of matter, like hyperons or even quark-gluon plasma, where quarks become unbound in a free state. The existence of these states pushes the boundaries of what we understand about the fundamental forces at play in the universe. Observations of neutron stars, particularly through the study of their gravitational waves or electromagnetic emissions, provide insight into their properties. For instance, as we observe neutron stars merging, we see how these colossal events produce heavy elements like gold and platinum through rapid nuclear processes. Such discoveries enrich our understanding of not only neutron stars but also the life cycle of matter itself throughout the cosmos. Neutron stars are cosmic laboratories revealing the nature of matter under extreme gravitational pressures, exposing the limitations of our current theories and urging scientists to revisit the foundations of physics and nuclear interactions. They embody a remarkable intersection of astrophysics and fundamental physics, continuously challenging our collective knowledge of the universe. Recent discoveries concerning neutron star collisions have transformed our understanding of cosmic events and their repercussions throughout the universe. Neutron stars, the remnants of massive stars that have undergone supernova explosions, are incredibly dense, with a spoonful weighing as much as an entire mountain. When two of these colossal objects collide, the event produces a cataclysmic explosion known as a kilonova, which generates an immense amount of energy and releases heavy elements into space, including gold and platinum. The observations of such collisions mark a significant advancement in astrophysics. When astronomers first detected gravitational waves, ripples in space-time caused by these merging neutron stars, it's as if they tapped into a new form of cosmic communication. This discovery, captured in 2017, not only validated a long-standing theory, but also opened a window into a completely different realm of observing the universe. Coupled with electromagnetic signals like light, researchers now have a multisensory platform to understand these dramatic cosmic events much more thoroughly. Furthermore, scientists have identified that the energy emissions and resulting phenomena from these collisions can help answer fundamental questions about the nature of gravity, the formation of elements, and the very fabric of space-time. Each collision serves as a cosmic laboratory that contributes to our knowledge of extreme physics, helping to piece together the landscape of the universe and our origins within it. The combination of gravitational wave data and light observed from kilonovae now helps reveal the mysteries of how the universe functions on a grand scale. As such, these discoveries are only the beginning, promising vast insights into the universe's most powerful and enigmatic processes. The idea of extra dimensions beyond our perceivable universe has captured the imagination of scientists and laypeople alike. One of the most prominent concepts arises from string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in multiple ways, but in order for the full range of their behavior to exist, additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time are necessary. The theory typically proposes that there are 6 or 7 extra dimensions, curled up and hidden from our direct observation, making them incredibly challenging to detect. Another intriguing framework is that of brain-world cosmology, which stems from string theory as well. In this view, our observable universe could be likened to a 3-dimensional surface or brain floating within a higher dimensional space. Events occurring in these additional dimensions might influence the physical laws and phenomena we experience, even if we cannot directly observe them. Additionally, some theories in theoretical physics, like quantum gravity models, explore the implications of more than 4 dimensions by examining how gravity might behave differently when considered in a higher dimensional context. These models seek to reconcile the seemingly separate realms of quantum mechanics and general relativity, hinting that our universe may be part of a more complex structure than we can currently perceive. Finally, ideas such as the multidimensional landscapes in cosmological theories suggest that our universe is just one of many possible configurations existing within a higher dimensional space, akin to a bubble among countless others. Each of these bubbles could have distinct physical laws and constants, further broadening the scope of what we might view as our reality. These theories push the boundaries of our understanding, proposing that the universe may be far more intricate than our everyday experiences suggest, encouraging scientists to explore the nature of existence beyond the limits of current perception. The concept of extra dimensions suggests that there are more spatial dimensions beyond the 3 we experience daily. Traditionally, we understand space as having length, width, and height, but theories in physics, notably string theory, propose the existence of additional dimensions that could be compacted or hidden from our view. This idea fundamentally alters our understanding of the universe and the laws governing it. Picture the familiar 3-dimensional world. Now, imagine that there are additional dimensions curled tightly, so small that they escape detection at our scale. These extra dimensions can influence the fundamental forces and particles we observe. For instance, they can provide new pathways for gravity to strengthen or weaken, potentially explaining why gravity seems so weak compared to other forces like electromagnetism. In a universe with extra dimensions, gravity could disperse into these dimensions, making it less potent in our familiar three-dimensional space. Moreover, the presence of extra dimensions could lead to new particles and interactions, modifying the standard model of particle physics. Such changes might help us understand phenomena like dark matter or dark energy, which remain elusive in current theories. When particles are allowed to move in additional dimensions, their behaviors could shift dramatically, offering explanations for things we cannot yet fully explain. Extra dimensions might also provide insights into the early universe, particularly during events like the Big Bang. The conditions of that time could have triggered interactions that play out differently based on how many dimensions were involved. In this sense, extra dimensions might not only affect current laws, but could also reshape our understanding of the universe's history and its ultimate fate. By exploring these hidden dimensions, we venture into uncharted territories of physics, where the established rules of reality bend and twist, opening possibilities for new physics that could one day rewrite our definition of the cosmos. Scientists are venturing into the mysterious territory of extra dimensions, guided by theories that suggest our universe might have more spatial dimensions than the three we experience daily. One primary approach involves particle colliders, like the Large Hadron Collider. Here, protons are accelerated to nearly the speed of light and smashed together. When they collide, these experiments unleash vast amounts of energy, which can, in theory, create tiny black holes or other particles that reveal the existence of extra dimensions. If these phenomena appear in the data collected, it could be a groundbreaking confirmation of higher dimensions. Another avenue of exploration involves gravitational wave detection. When two massive objects, such as black holes, collide, they produce ripples in space-time. By studying these waves, scientists hope to uncover anomalies that suggest the influence of extra dimensions on gravity and how it behaves. The existence of additional dimensions could alter the characteristics of these waves, providing crucial hints about their presence. Additionally, researchers are investigating certain types of cosmic rays and their interactions in the atmosphere. When high-energy particles from space collide with atoms in the Earth's atmosphere, they can produce showers of secondary particles. Analyzing these interactions might provide indirect evidence for extra dimensions if the results consistently deviate from expected patterns. All of these experiments share one critical goal: to provide a deeper understanding of the fundamental fabric of the universe. By identifying signs of extra dimensions, scientists could reshape our perception of reality, bridging gaps between known physics and the unknown realms that lie beyond our familiar three-dimensional world. Extra dimensions play a pivotal role in string theory, which is a leading framework attempting to unify our understanding of fundamental forces and particles. To grasp their significance, envision our familiar three-dimensional world, where we can move left, right, forward, backward, up, and down. However, string theory proposes that the universe might have more dimensions, usually posited as additional hidden dimensions that are compactified, meaning they are curled up so small we can't perceive them in everyday life. These extra dimensions are essential for several reasons. First, they provide the necessary framework for strings, which are the fundamental building blocks in string theory. In this view, particles are not point-like objects, but rather tiny vibrating strings. The different vibrations of these strings correspond to different particle types, similar to how the strings on a musical instrument produce various notes. The properties of these particles, including mass and charge, are influenced by how these strings interact with the extra dimensions. Moreover, extra dimensions help reconcile gravity with the other fundamental forces. In our four-dimensional perspective, 3 dimensions of space and 1 of time, gravity behaves differently compared to forces like electromagnetism. By incorporating additional dimensions, string theory offers a more comprehensive picture where gravity can be described alongside other forces, potentially addressing phenomena that current models cannot explain, such as the behavior of black holes or the conditions of the very early universe. Additionally, hidden dimensions may provide clues about why our universe appears fine-tuned and why certain constants of nature have the values they do. These extra dimensions enrich the fabric of string theory, giving it the flexibility to model the complexities of our universe, consequently paving the way for a deeper understanding of the cosmos. The idea of extra dimensions opens up a fascinating new perspective on the structure of the universe. Traditionally, we experience the world in three spatial dimensions: length, width, and height, plus time. However, theories suggest that beyond these familiar dimensions, there could be additional ones intricately woven into the fabric of reality. Imagine our three-dimensional world as a sheet of paper, flat and straightforward. If extra dimensions exist, they might be like folds or wrinkles on that paper, hidden from our direct view yet influencing everything we see. These extra dimensions could be compact and curled up, so small that they remain unnoticed in our daily lives, or they might act as pathways connecting different points in our universe in ways we have yet to comprehend. If extra dimensions are real, they could help explain some of the universe's most perplexing mysteries, such as the behavior of gravity compared to other fundamental forces. In many theories, gravity is relatively weak, but with extra dimensions, gravity might spread out across these additional spaces, making it appear weaker to us while remaining powerful at a larger scale or over longer distances. Moreover, this concept opens up the possibility of new physical phenomena. Imagine particles moving through these extra dimensions. They could interact in unexpected ways or possess properties that defy our current understanding. Such interactions could lead to novel forms of matter or energy that enrich the cosmic tapestry. Recognizing the potential existence of extra dimensions could dramatically reshape our grasp of physics, leading to a more comprehensive theory that unites gravity with the other forces of nature and deepens our insight into the universe's architecture. It invites us to reconsider the limits of our reality, suggesting that the cosmos is far more intricate than it appears at first glance. Cosmic rays are high-energy particles that travel through space and reach Earth from various sources, including the Sun and distant cosmic events like supernovae or black holes. Think of them as tiny messengers carrying information from the farthest reaches of the universe. These particles primarily consist of protons, but they can also include heavier atomic nuclei and even some electrons. The significance of cosmic rays in space exploration lies in the insights they provide about the universe's workings. When these energetic particles collide with the atmosphere, they produce showers of secondary particles that can be detected by specialized instruments. This interaction allows scientists to study the composition of cosmic rays, their origins, and the processes that accelerate them to such extreme speeds. Cosmic rays serve as a window into high-energy astrophysics. By analyzing their spectra and behavior, researchers can infer the physical conditions of their sources and the nature of the galactic and intergalactic environments. They also play a role in understanding fundamental questions about the universe, such as matter-antimatter asymmetry and the dynamics of cosmic evolution. Moreover, cosmic rays can affect both the Earth's atmosphere and human technology, including spacecraft. Understanding how these particles interact with the atmosphere is essential for studying climate changes over geological timescales. In addition, for future space missions, knowledge of cosmic radiation helps in designing protective measures for astronauts, ensuring their health and safety during long-duration flights beyond Earth's protective atmosphere. By studying cosmic rays, we unlock not just the mysteries of the universe, but also safeguard our ventures into the extensive unknown. Cosmic rays are enigmatic particles that travel through space at nearly the speed of light, creating intrigue in the scientific community. They are primarily composed of protons, which are the building blocks of atomic nuclei, but they can also include heavier atomic nuclei and even electrons. These high-energy particles continually bombard the Earth from all directions, originating from various sources across the universe. One of the greatest mysteries surrounding cosmic rays is their origin. While some cosmic rays are believed to come from our own sun, the more energetic ones seem to have sources far beyond, possibly within supernova remnants, explosions of massive stars. These supernovae can produce shock waves that accelerate particles to extraordinary speeds. Other potential sources may include active galactic nuclei, where supermassive black holes consume material in a dramatic fashion, and gamma-ray bursts, which are among the most energetic events known. Another layer to this mystery revolves around the composition of these rays. While it is generally accepted that most cosmic rays are protons, the exact ratios of different particles and their energies remain poorly understood. Scientists need to discern how these cosmic particles maintain their energy levels over vast distances and through the dense magnetic fields they encounter. The interactions between cosmic rays and the interstellar medium, which is the matter that exists in the space between stars, also play a critical role in shaping the characteristics of these rays as they travel through space. Furthermore, cosmic rays challenge our understanding of the fundamental physics that governs particle acceleration and propagation in space. The mechanisms through which these particles gain such immense energy are still being investigated. This quest for knowledge is essential, as cosmic rays can impact space weather and even affect technological systems on Earth. Understanding them helps us unlock the broader narratives of cosmic events and the evolution of the universe itself. Each new discovery regarding cosmic rays peels back a layer of the complex tapestry of our cosmos, revealing more about the forces at work in the grand scheme of existence. Cosmic rays are high-energy particles that travel through space and occasionally strike the Earth. These particles mostly come from sources outside our solar system, including exploding stars and supernova. When they enter our atmosphere, cosmic rays can have various effects on life and the environment. The interaction of cosmic rays with the Earth's atmosphere produces secondary particles and radiation. While our atmosphere acts as a protective shield, absorbing and deflecting many of these incoming particles, some do reach the surface. This radiation can influence biological processes, but for the most part, it doesn't pose a significant threat to human health under normal circumstances. One notable impact is the potential for increased mutation rates in living organisms. Cosmic rays can interact with DNA, causing changes that may lead to mutations. While most mutations are harmless and even beneficial, some can result in diseases, including cancer. However, it's essential to emphasize that the rate of these mutations is still relatively low, and our bodies have mechanisms to repair DNA damage effectively. In a broader ecological context, cosmic rays can influence atmospheric chemistry, which indirectly affects climate and weather patterns. They play a role in the formation of aerosols, tiny particles that serve as nuclei for cloud formation. Changes in cloud cover can influence climate by altering temperature and precipitation patterns. Interestingly, there is a scientific hypothesis that cosmic rays might influence the behavior of life on Earth through their effects on the environment. Some researchers propose that increased cosmic ray activity could lead to changes in cloud cover, potentially affecting everything from plant growth to animal migration patterns. These ideas are part of ongoing studies exploring the interconnectedness of cosmic phenomena and terrestrial life. While the majority of cosmic rays are filtered by our atmosphere and have minimal direct impact on human health, they play a complex role in influencing life on Earth through mutation, ecological changes, and potentially altering weather patterns. Their effects remind us of the dynamic relationship between outer space and the intricacies of life on our planet. Ultra-high-energy cosmic rays are among the most energetic particles known to exist in the universe, with energies far exceeding those achievable by human-made accelerators. Their significance lies in both their extreme nature and the mysteries they present. These cosmic rays, primarily protons or atomic nuclei, originate from distant astrophysical sources, which are yet to be fully understood. When these particles reach the Earth, they carry valuable information about their origins and the processes that produce them. The sheer energy of ultra-high-energy cosmic rays suggests that they are associated with some of the most powerful events in the cosmos, such as supernova explosions, collisions of massive celestial bodies, or even the centers of galaxies that house supermassive black holes. Understanding where they come from can provide insights into the most violent and energetic phenomena taking place in the universe. As they interact with the atmosphere, ultra-high-energy cosmic rays create a cascade of secondary particles, contributing to atmospheric science and providing a unique opportunity to study high-energy physics. Observations of these interactions help physicists explore fundamental questions regarding particle physics, including the properties of matter and the nature of the forces that govern it. Moreover, studying these cosmic rays can also unveil new aspects of the universe, including the mechanics of cosmic evolution and the role of magnetic fields that influence their path through space. Each ultra-high-energy cosmic ray is not merely a particle, but a piece of cosmic history, a messenger from the farthest reaches of the universe that adds to our understanding of its complexity and the forces that shape it. Their significance, therefore, is not just in their energy, but in the multitude of secrets they hold about our universe. Cosmic rays are high-energy particles that travel through space and can originate from various sources, such as supernovae or distant galaxies. Their study opens a window into the workings of the universe, illustrating the dynamic processes that shape it. Imagine these particles as messengers from the farthest reaches of space, arriving at Earth with stories about their origins and the environments they've traversed. As cosmic rays interact with the Earth's atmosphere, they produce secondary particles, which cascade downwards and can be detected by ground-based observatories. By analyzing these interactions, scientists can unravel critical details about the fundamental forces at play in the universe. For instance, researchers can gain insights into the composition of distant cosmic events, the energy production mechanisms of stars, and even the nature of dark matter. Every elemental composition and energy level of these rays can tell us something unique about celestial bodies, such as whether they are undergoing explosive events or stable processes. Furthermore, cosmic rays offer clues about extreme cosmic conditions, including high-energy environments that are not replicable in laboratories. Understanding cosmic rays also helps in assessing their potential effects on both human endeavors and technological infrastructure. As these particles bombard Earth, they can interfere with satellites and pose risks to astronauts in space. Thus, studying them not only enriches our knowledge of the cosmos, but also serves as a critical element for safeguarding our activities beyond our atmosphere. By decoding the enigma of cosmic rays, we unlock layers of knowledge about the universe's past, present, and future. Quantum mechanics introduces a fascinating layer to our understanding of the universe, revealing that at a fundamental level, everything around us operates under rules that often defy our everyday experiences. While classical physics describes larger objects with predictable paths and behaviors, quantum mechanics deals with the tiniest particles, such as atoms and subatomic particles, where uncertainty and probability reign supreme. In the world of the very small, particles do not have definite positions or speeds until they are measured. Instead, they exist in a state of possibility. This concept parallels our observations of the cosmos, where certain phenomena, like the behavior of light and gravity, also seem to showcase dualities and paradoxes at larger scales. For instance, light can behave as both a particle and a wave, illustrating that the boundaries between different states can often blur. One significant intersection of quantum mechanics and cosmology occurs in the study of black holes. When matter is compressed into a black hole, it creates an environment where the laws of quantum mechanics must be applied alongside those of general relativity, which describes gravity's influence on the fabric of space and time. This combination raises intriguing questions, such as what happens to information that falls into a black hole. Some theories suggest that information is not lost, existing in a sort of holographic format on the event horizon, while others push for new physics to explain this paradox. Another exciting aspect is the concept of quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, no matter how far apart they are. This phenomenon challenges our traditional notions of locality and causality and hints at the potential for a deeper, interconnected structure of the universe. Furthermore, as scientists theorize about the early moments of the universe, quantum mechanics plays a critical role in understanding the conditions under which the cosmos emerged. The rapid expansion called cosmic inflation, theorized to have occurred just after the Big Bang, suggests that quantum fluctuations could have led to the vast and intricate structure of galaxies we observe today. Thus, merging quantum mechanics with cosmological models invites us to rethink our perceptions of reality and opens the door to new scientific revelations. As we continue to explore these connections, we may uncover answers to some of humanity's most profound questions about the very nature of existence. Quantum entanglement presents one of the most fascinating and perplexing puzzles in modern physics. At its core, entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter how vast the distance between them. Imagine having two dice that are entangled. If you roll one and it shows a 6, the other will simultaneously show 6 as well, regardless of whether it's in the same room or on the other side of the universe. This mysterious connection raises profound questions about the nature of reality and our understanding of space and time. For instance, it challenges the very concept of locality, which is the idea that objects only directly influence their immediate surroundings. If particles can be entangled over massive distances, what does that suggest about the fabric of our universe? Are there hidden dimensions or forces at play that allow such instantaneous communication, defying the limits imposed by the speed of light? The implications of quantum entanglement extend beyond theoretical considerations. They have practical applications in fields like quantum computing and cryptography, potentially revolutionizing technology. However, despite these advancements, many mysteries remain unsolved. For example, why do certain particles become entangled in the first place? What role does an observer play in determining the state of these entangled particles? On a cosmic scale, considering entanglement raises questions about the interconnectedness of everything in the universe. Could it imply that all matter is fundamentally linked, creating a web of connections beyond our comprehension? As scientists continue to explore quantum mechanics, they seek to unravel these mysteries, searching for answers that could fundamentally reshape our understanding of the universe. Quantum mechanics opens a fascinating window into understanding black holes by revealing how the tiniest building blocks of our universe might interact with these colossal entities. Traditionally, black holes are defined by their immense gravity, which pulls in everything, including light, from vast distances. However, at the quantum level, things behave in ways that often defy our classical understanding. One of the key insights from quantum mechanics is the concept of uncertainty. This principle suggests that we cannot know both a particle's position and momentum with absolute precision. Near a black hole, this uncertainty leads to intriguing possibilities. Particles can spontaneously appear and disappear, a process often referred to as quantum fluctuations. These fluctuations mean that even in the extreme environment around a black hole, matter and energy are never completely at rest or completely absent. Another significant concept is Hawking radiation, theorized by physicist Stephen Hawking. This phenomenon posits that black holes might not be entirely black, but instead could emit radiation due to quantum effects near their event horizon. When particle-antiparticle pairs form just outside the event horizon, one may fall into the black hole while the other escapes, resulting in a tiny amount of radiation that, over vast periods, could lead to the evaporation of the black hole itself. Furthermore, quantum mechanics leads to discussions about information. In classical physics, anything that falls into a black hole is lost forever, but quantum theory suggests that information cannot be destroyed. This ongoing debate about what happens to information in a black hole could reshape our understanding of reality and the fundamental laws governing the universe. By intertwining quantum mechanics with black hole physics, scientists address some of the most profound mysteries of the cosmos, including the relationship between gravity and quantum forces. As researchers continue to explore this intersection, we unravel layers of complexity, challenging what we think we know about black holes and our universe as a whole. In the vast emptiness of space, the vacuum is not as empty as it seems. Instead of being a void, it's teeming with what are known as virtual particles. These fleeting entities emerge from the energy fluctuations occurring in the vacuum. According to quantum mechanics, energy and matter are interconnected, allowing for particle-antiparticle pairs to spontaneously appear for an incredibly brief time before annihilating each other. Think of virtual particles as ephemeral guests at a cosmic party. They pop into existence, perhaps exchanging energy or exerting fleeting influences on other particles, before disappearing just as quickly as they arrived. Although they are incredibly short-lived, these virtual particles are fundamental because they contribute to the forces that act on real particles around them, like giving rise to the forces of gravity and electromagnetism. Additionally, virtual particles play a pivotal role in processes such as Hawking radiation, where they contribute to the phenomenon observed around black holes. When one of these particles escapes from the gravitational pull of a black hole while its partner falls in, it effectively leads to a gradual loss of the black hole's mass. This illustrates how even in the vast emptiness of space, these seemingly insubstantial particles are woven into the very fabric of the universe, affecting everything from the behavior of light to the fate of massive celestial bodies. The influence of virtual particles showcases the intricate and dynamic nature of the vacuum, revealing that even the emptiest regions are alive with activity. The principles of quantum mechanics offer intriguing insights into the origins of our universe. At its core, quantum mechanics deals with the behavior of tiny particles at the smallest scales, where the rules can seem counterintuitive. One of its fundamental aspects is the idea of uncertainty. Particles do not have definite positions or velocities until they are measured. This leads to the concept that multiple possibilities can coexist simultaneously. Now, when we consider the origin of the universe, particularly the moment that is often referred to as the Big Bang, quantum mechanics becomes essential. Before this event, it is theorized that the universe existed in an incredibly compact state where quantum effects dominated. In this primordial environment, fluctuations in energy could occur spontaneously, leading to variations that might have given rise to the universe as we know it. These fluctuations could result in small pockets of energy that expand, giving birth to matter and radiation as the universe started to cool. In this way, quantum mechanics suggests that the very fabric of the universe may have emerged from a chaotic tapestry of possibilities at the quantum level. Furthermore, theories like quantum inflation extend these ideas, proposing that during a brief moment after the Big Bang, the universe underwent a rapid expansion fueled by quantum energy fluctuations. This not only explains the uniformity of the cosmos we observe today, but also the distribution of galaxies and large-scale structures we see throughout the universe. Ultimately, the interplay between quantum mechanics and cosmology remains a frontier of modern physics, seeking to unravel the deep mysteries of how everything began from a realm governed by probabilities and uncertainties. This exploration invites us to rethink our understanding of reality itself, revealing that the universe's origins may lie within the heart of quantum phenomena. Galaxy formation and evolution remain among the most tantalizing puzzles in astrophysics. To understand this mystery, we need to start at the very beginning of the universe, just after the Big Bang. Following this event, the universe was a hot, dense place filled with hydrogen and helium. As it expanded, regions of gas began to cool and clump together under gravity. One of the intriguing questions is how these initial clusters grew into the vast galaxies we see today. Some theories suggest that dark matter, which is a type of matter that does not emit light and is detected only through its gravitational influence, played a crucial role. It is theorized that dark matter formed a scaffold in the early universe around which visible matter would accumulate. This means that galaxies may have formed in the gravitational wells created by dark matter, leading to the rich variety of shapes and sizes we observe. Additionally, we face questions about the specific processes that led to the variety of galaxy types, from spiral to elliptical. Does the environment, such as density and interaction with other galaxies, affect their structure and evolution? There is also the role of star formation. How did initial bursts of star creation impact the host galaxy's structure? For example, some galaxies are actively forming new stars, while others have gone quiet long ago. Another enigma is the fate of galaxies. Over billions of years, some galaxies merge, leading to hybrid structures, while others may experience significant changes due to external forces or internal processes, like galactic winds. These interactions can trigger new waves of star formation or quench it entirely, showing that the journey of a galaxy is as much about its history of relationships with neighbors as it is about its own individual development. Lastly, the role of supermassive black holes at the centers of galaxies complicates the picture even further. These immense objects might influence the growth and evolution of galaxies, affecting star formation rates and the dynamics of surrounding stars and gas. The precise connection between black hole growth and galaxy evolution is still an open question, inviting ongoing research. The mysteries of galaxy formation and evolution intertwine questions about dark matter, star formation, environmental influences, and the evolution occurring over cosmic timescales. Each discovery in this field not only brings us closer to understanding our universe, but also reveals the intricate tapestry of forces and interactions that shape the very fabric of the cosmos. Observations of galaxy rotation curves present a fascinating challenge to existing theories of astrophysics. When astronomers study a galaxy, they measure how fast stars and gas are rotating around its center at various distances. According to classical physics and the behavior of visible mass, we expect the rotation speed to decrease with distance from the galactic center, much like how planets in our solar system move slower the farther they are from the sun. However, observations reveal something quite different. In many galaxies, the rotation speeds remain constant or even increase as you move further out from the center. This discrepancy is problematic because it implies that there is more mass present than we can see. Conventional matter, like stars and gas, simply doesn't account for this extra gravitational influence. This has led scientists to propose the existence of dark matter, an invisible substance that doesn't emit light or energy, making it incredibly difficult to detect directly. Dark matter is thought to make up a significant portion of the total mass in the universe, providing the additional gravitational pull needed to account for the observed rotation speeds. This revelation has shifted the way we understand matter in the cosmos, suggesting that most of the universe's mass is hidden from our view. The challenge lies not only in confirming the presence of dark matter, but also in understanding its nature and how it interacts with regular matter. This mystery fundamentally alters our comprehension of gravitational dynamics, the evolution of galaxies, and the overall structure of the universe, leaving scientists to continuously refine their theories and models to incorporate these surprising observations. In the vast cosmos, one intriguing enigma lies in the observation that galaxies contain much less visible matter than we would anticipate. While a galaxy appears adorned with stars, gas, and dust, calculations suggest there's a significant portion of matter that remains unseen. This phenomenon raises essential questions about what constitutes this missing matter. Astrophysicists estimate that visible matter, the kind we observe through telescopes, makes up only a small fraction of a galaxy's total mass. The rest is thought to consist of dark matter, a mysterious substance that does not interact with light or electromagnetic forces, making it invisible. Dark matter's presence is inferred from its gravitational effects on visible matter. For example, galaxies rotate at speeds that should cause them to tear apart if only the visible matter were present. Yet, they hold together, suggesting an unseen force, this dark matter. Despite extensive studies, pinpointing the nature of dark matter remains elusive. It could consist of exotic particles that we have yet to detect, possibly hinting at entirely new physics. Some theories even propose that instead of dark matter, modifications to our understanding of gravity might explain these discrepancies. The questions multiply as researchers explore the distribution of missing matter within galaxies. Why isn't it uniformly distributed? Could this missing matter be clumping together in regions we cannot examine? Additionally, the mystery extends beyond our galaxies. Observations suggest that the universe itself is expanding, and mapping the distribution of matter in various celestial structures such as galaxy clusters reveals intriguing patterns that don't align with our current models. As scientists delve deeper into this puzzle, they leverage advanced technology like powerful telescopes and particle detectors, aiming to uncover the secrets hidden within the cosmos. Each discovery leads to more questions, transforming the search for missing matter into a thrilling journey through the depths of the universe, as we strive to understand not just what is out there, but the very nature of reality itself. The interactions between galaxies frequently defy our expectations in several intriguing ways. When we think about galaxies, we often envision them as isolated entities drifting through the cosmos. However, space is not as empty as it might seem. Galaxies are constantly on the move and frequently come close to each other, leading to gravitational interactions that can be surprising. For instance, when two galaxies approach each other, they don't just pass by like ships in the night. Instead, their gravitational forces pull at one another, leading to dramatic distortions in their shapes. This can create long tidal tails, which are streams of stars and gas that stretch away from the original galaxies, sometimes even forming new stars as interstellar matter collides and compresses. Such interactions can lead to merging, where two galaxies combine to form a larger one, fundamentally altering their structures and star formation rates. Another surprising aspect is that these interactions can ignite periods of intense star formation, known as starbursts. The gravitational effects can funnel gas into the center of galaxies, causing stars to form at rates far exceeding what is typical for an isolated galaxy. This means interactions can make galaxies temporarily more vibrant and active than they would otherwise be, often leading to an unexpected burst of brightness observable across great distances. Moreover, the dynamics of these encounters can lead to complex outcomes that challenge our understanding of galactic evolution. Sometimes, rather than merging completely, galaxies will pass by each other and then separate, leaving behind lingering gravitational influences that can affect their movement for millions of years. Additionally, the phenomenon of dark matter complicates these interactions. Dark matter is an invisible component that doesn't emit light but influences the motion of stars and gas. Its presence means that the gravitational pull felt by galaxies during interactions is far more complex than visible matter alone would suggest, leading to unexpected behaviors in their orbits and interactions. Overall, the interactions between galaxies reveal a dynamic and intricate universe where nothing is truly predictable. They continuously reshape the cosmos and offer new insights into the formation and evolution of galaxies in ways that keep scientists on their toes. The diverse shapes of galaxies provide valuable insights into the processes that govern our universe. When we look at the many galaxies scattered across the cosmos, we notice a range of formations from spirals with elegant arms to irregular ones that appear distorted and chaotic. These unusual shapes often tell a story of their formation and interaction with other celestial bodies. Galaxies don't exist in isolation. They are part of a dynamic and evolving environment. The gravitational pull between them plays a crucial role in shaping their structure. For instance, when two galaxies collide, their gravitational forces can dramatically alter each other's forms. This interaction might stretch one or both galaxies into bizarre shapes, leading to new star formation in the areas where gas clouds collide. The process not only alters their appearances, but can also trigger bursts of star birth as gas is compressed, leading to regions of intense brightness. Additionally, galaxies can be influenced by their surroundings through processes known as tidal interactions. Imagine two massive bodies in water. Each movement creates ripples that interact with and influence one another. Similarly, as galaxies pass close to one another, their mutual gravitational attraction can twist and pull them into unique shapes, revealing the history of their interactions. Moreover, the irregularity often seen in certain galaxies can suggest a relatively younger phase in their life cycle. Galaxies evolve over billions of years, and their shapes can indicate ongoing processes like mergers, collisional events, or the impacts of dark matter, a mysterious form of matter that does not emit light or energy. The presence and distribution of dark matter can exert immense gravitational effects, influencing how galaxies form and interact. Overall, the unusual shapes of galaxies serve as cosmic fingerprints. They reveal not only how galaxies were shaped by their formation and evolutionary paths, but also illuminate the gravitational dance that continues to unfold across the universe. Understanding these shapes allows scientists to piece together the grand narrative of cosmic history, shedding light on the forces and phenomena that have sculpted the universe we see today. The search for extraterrestrial intelligence is an exciting and multifaceted endeavor that seeks to answer one of humanity's most profound questions. Are we alone in the universe? Several promising strategies enhance our quest for signs of life beyond our planet. One of the primary approaches is the use of radio telescopes to listen for signals. This strategy is based on the idea that advanced civilizations might use radio waves to communicate, much like we do. By scanning the cosmos for unusual or repeating signals, scientists hope to catch a message from these distant intelligences. It's akin to tuning into a radio station, where the right frequency can reveal an extraordinary broadcast from far away. Another crucial strategy is the exploration of exoplanets, planets that orbit stars beyond our solar system. Scientists analyze data from space telescopes to identify candidates in the so-called habitable zone, where conditions may be right for liquid water, a key ingredient for life as we know it. This involves studying the atmospheres of these planets for signs of gases that could indicate biological processes, such as oxygen or methane, which are often associated with life. Additionally, the search extends to sending our own messages into the cosmos, known as active SETI, or the search for extraterrestrial intelligence. This method involves transmitting signals that convey information about humanity and Earth in hopes that an advanced civilization might respond. It's a bold step, taking the initiative to reach out rather than simply waiting to receive. The use of advanced artificial intelligence tools enhances our search capabilities. These technologies can analyze vast amounts of data far more efficiently than humans can, allowing scientists to identify patterns and signals that might suggest extraterrestrial activity. Finally, the study of extremophiles, organisms that thrive in extreme environments on Earth, may provide insights into the types of life that could exist elsewhere. By understanding the resilience of life in extreme conditions, we refine our criteria for habitability and the potential diversity of extraterrestrial organisms. Each of these strategies contributes to a larger framework of discovery, representing humanity's yearning to comprehend our place within the cosmos. Through perseverance and innovation, the search for extraterrestrial intelligence continues to inspire hope and curiosity about the universe's endless possibilities. Scientists estimate the probability of life existing beyond Earth through a multifaceted approach that combines astronomy, biology, and statistics. One of the primary frameworks is known as the Drake equation, which attempts to quantify factors linked to potential extraterrestrial civilizations. This equation considers various variables, including the rate of star formation in our galaxy, the number of stars that may host planets, and the fraction of those planets that might have conditions suitable for life. To develop these estimates, researchers examine the vast array of exoplanets, planets outside our solar system, identified through telescopes and other observation methods. They focus on the habitable zone around stars, where conditions could support liquid water, a fundamental ingredient for life as we know it. Scientists have discovered that many stars possess a plethora of planets, some located in these zones, greatly enhancing the prospects for life. Astrobiologists also look at extremophiles, organisms on Earth that thrive in incredibly harsh environments, such as deep-sea vents or arid deserts. These forms of life help scientists redefine what conditions may be suitable for life elsewhere, suggesting that life could exist in forms and environments previously considered inhospitable. Moreover, other factors, such as the chemical makeup of a planet's atmosphere or the presence of essential elements like carbon, oxygen, and nitrogen, are scrutinized. Researchers analyze data from space missions and telescopes to gather evidence about these elements, providing further insight into the potential for life. Finally, statistical models come into play, using all gathered data to calculate the likelihood of life. By incorporating information from many sources, scientists can begin to assess how frequently life might arise under different scenarios across the universe. This ongoing research and synthesis of findings underlies the compelling search for life beyond our world, shaping our understanding and expectations of life in the cosmos. The signals we receive from space are full of intrigue and scientific potential, encompassing everything from radio waves to light. One of the most captivating mysteries involves bursts of radio waves known as fast radio bursts. These occur with such intensity that in a fraction of a second they can unleash a tremendous amount of energy, comparable to what the sun emits in an entire day. Yet their exact origins remain a puzzle. Some scientists speculate they could be related to highly energetic cosmic events, while others suggest they might be signals from advanced civilizations. Another layer of mystery is woven into cosmic background radiation, the faint afterglow of the Big Bang. This radiation presents a snapshot of the universe when it was just a fraction of its current age. Analyzing these signals helps researchers understand the formation and evolution of galaxies, but the precise details and implications of the variations within this radiation continue to generate questions. Additionally, the study of gravitational waves, ripples in space-time caused by massive celestial events like black hole collisions, has illuminated new territories of understanding. When these waves reach Earth, they carry information about the events that created them. Understanding these signals not only gives us insights into the behavior of the universe, but also hints at the very fabric of space-time itself. Moreover, the concept of extraterrestrial signals adds another layer of excitement. Efforts to detect signs of intelligent life through initiatives like the search for extraterrestrial intelligence strive to find patterns or structured signals among the noise of cosmic background radiation. Each strange signal detected invites speculation and analysis, with the potential to change our comprehension of life beyond our planet. The signals flooding our planet from the cosmos are more than just noise. They are whispers from the universe, carrying secrets about the formation, structure, and perhaps even the inhabitants of our expansive cosmic neighborhood. Each discovery, however small, pulls the thread of comprehension tighter, leading researchers deeper into the intriguing unknown. The discovery of alien life would be a revolutionary moment in humanity's understanding of existence itself. For centuries, we have pondered whether we are alone in the vast cosmos, and finding life beyond Earth would serve as profound validation of the idea that life is not a solitary phenomenon. It would suggest that the building blocks of life, perhaps simple molecules and essential elements, can combine in diverse environments across the universe, hinting at a universal recipe for life. If we were to encounter life forms, whether microbial or advanced, it would challenge our perception of biology, evolution, and the conditions necessary for life to thrive. Scientists would need to reconsider the factors that define habitability. It is entirely possible that life elsewhere has adapted to environments radically different from our own, existing in extreme temperatures, high radiation, or even entirely different chemical bases. This would expand our understanding of what life can be and the myriad forms it might take, breaking down the barriers of what we thought was essential for survival. Furthermore, alien life would spur new philosophical and ethical discussions about our place in the universe. It would prompt questions about communication, cooperation, and even the potential for conflict with other intelligent beings. Our assumptions about evolution, intelligence, and social structures would be tested. The discovery would also reignite interest in space exploration and research into astrobiology, the study of life in the universe. Our searches would become more focused, targeting environments in outer space that might harbor life, such as the icy moons of distant planets or the atmospheres of exoplanets. Finding alien life would not merely be a scientific achievement, it would be a turning point that alters our worldview, reshaping our understanding of biology, evolution, and ultimately what it means to be human in an interconnected, alive universe. Detecting biosignatures on exoplanets presents a multitude of challenges that researchers grapple with. Firstly, exoplanets are incredibly distant, often many light years away from Earth. This vast emptiness means that gathering light and data from them is inherently difficult. Even when we do receive light from these planets, it is minute and often mixed with the overwhelming brightness of their host stars. In addition to distance, the complexity of differentiating signals adds another layer of difficulty. Biosignatures, which are indicators of life, can take various forms, such as specific gases in an atmosphere. However, many of these gases can also be produced by non-biological processes. For example, methane could signal life or be the result of geological activity. Identifying whether a gas is of biological origin or not necessitates precise analysis and often sophisticated models to interpret the data accurately. Instrument limitations are another significant hurdle. Current telescopes and sensors must be incredibly sensitive to detect the faint signatures amidst the glare of stars. Instruments designed for this task are still being developed, and achieving the necessary sensitivity and resolution to analyze exoplanet atmospheres is a significant challenge for scientists. Weather and atmospheric conditions on these exoplanets can obscure potential biosignatures. Diverse atmospheres may act as filters, altering or masking signals before they reach our telescopes. Moreover, understanding the spectrum of light that passes through these atmospheres allows scientists to infer their compositions. But this is an inherently complex process. Lastly, the fundamental challenge of confirming a biosignature remains. Even if a potential biosignature is detected, the evidence must be compelling enough to distinguish it from false positives. The search for life beyond Earth is an intricate puzzle that requires advances in technology, comprehensive models, and ultimately, irrefutable data to confirm life exists elsewhere in the universe. Gamma-ray bursts are incredibly intense flashes of gamma rays, the most energetic form of electromagnetic radiation. These explosions can release more energy in just a few seconds than the sun will emit over its entire lifetime. They occur at great distances, often billions of light years away, making them some of the most powerful events in the universe. The mystery surrounding gamma-ray bursts lies in their origins and the exact mechanisms that cause them. There are two main types, those resulting from the collapse of massive stars and those resulting from the collision of neutron stars. In the first scenario, when a massive star runs out of fuel, it can collapse to form a black hole, triggering a violent explosion. The second scenario occurs when two neutron stars spiral toward each other and merge, resulting in a catastrophic release of energy. Though scientists understand these basic categories, many details about the processes involved remain elusive. Another puzzling aspect is the variability of these bursts. Some last just a fraction of a second, while others can last for several minutes, and their intensity can also vary greatly. This unpredictability has made them challenging to study, as astronomers must often rely on detecting the bursts after they've occurred. Additionally, since they happen far away, they serve as a glimpse into the conditions of the early universe, providing clues about the formation of celestial bodies and the overall evolution of cosmic structures over time. As researchers continue to unravel the mysteries of gamma-ray bursts, they not only learn about these incredible phenomena, but also gain insights into the fundamental laws of physics and the nature of the cosmos itself. Each discovery acts as a stepping stone to greater understanding, revealing the complex interplay of forces that govern the universe. The discovery of bursts, particularly fast radio bursts, presents intriguing challenges to existing astrophysical models. Traditionally, our understanding of the universe and its phenomena is built on a foundation that seeks to categorize and explain events through well-defined parameters and known sources. However, fast radio bursts occur with incredible intensity and brief duration, leaving little time for observation or detailed study. Astrophysicists had long regarded certain cosmic signals as either originating from known cosmic processes like pulsars or supernovae. Yet, fast radio bursts do not neatly fit into these categories. Their origin remains a mystery, causing scientists to reconsider the sources of such phenomena. The sheer power of these bursts, which can emit as much energy in a few milliseconds as our sun does in several years, pushes researchers to explore possibilities that could include exotic objects or even advanced technological sources from distant civilizations. Moreover, these bursts challenge conventional models of galaxy evolution and energy mechanisms within the universe. The environments from which fast radio bursts emerge are often not easily explained by existing models that assume a uniform distribution of matter and energy on cosmic scales. Understanding the conditions that could lead to such energetic emissions requires a shift in perspective. The implications go deeper into our understanding of gravity, radiation, and the behavior of matter in extreme conditions. Accepting that there could be gaps in our knowledge means that scientists must explore new theories that encompass not just the bursts themselves, but also the cosmic settings in which they occur. Every new burst offers potential insights, nudging astrophysical models to adapt, evolve, and broaden their scope to incorporate these captivating markers of the universe's complexity. Gamma-ray bursts, which are among the most powerful explosions in the universe, have intrigued scientists for decades. Current theories suggest that these bursts are primarily linked to two distinct cosmic events. The first scenario involves the collapse of massive stars. When such a star exhausts its nuclear fuel, it can undergo a supernova explosion, followed by the formation of a black hole. In some cases, as the star collapses, it emits jets of energy at near light speed. These jets release immense amounts of gamma rays and can be detected across vast distances, making them visible to our instruments. The second theory points to the merger of compact objects, specifically neutron stars. These neutron stars are the remnants of supernovae and are incredibly dense. When two neutron stars collide, the resulting event can generate intense gravitational waves and a powerful burst of gamma rays. This catastrophic merger not only results in the emission of gamma rays, but can also lead to the formation of a black hole, further contributing to the energetic landscape of the universe. Recent observations also suggest that not all gamma-ray bursts are the same. Long-duration bursts, which last from a few seconds to a few minutes, are typically associated with the collapse of massive stars. On the other hand, short-duration bursts, lasting only a few seconds, are often the result of neutron star mergers. This distinction has helped refine our understanding and allowed researchers to piece together a more comprehensive picture of these extraordinary phenomena. As we continue to develop our astronomical tools and techniques, the exploration of gamma-ray bursts unveils not just their origins, but also their role in the evolution of the universe, shedding light on the processes that govern the life and death of stars across the cosmos. Gamma-ray bursts are among the most energetic events in the universe, unleashing a staggering amount of energy in a matter of seconds, equivalent to what the sun might emit over its entire lifetime. When these bursts explode, they create powerful jets of radiation and matter that propel outward at nearly the speed of light. This dramatic release of energy fundamentally alters their surrounding environments in several profound ways. As the gamma-ray burst's energy spreads, it creates shock waves that collide with surrounding gas and dust. This interaction heats the matter up to millions of degrees, radiating light across various wavelengths, including X-rays and visible light. The shock waves can compress nearby gas, triggering the formation of new stars by concentrating material in specific regions. So rather than merely being destructive, gamma-ray bursts can foster creation amidst their chaos. In addition to immediate thermal effects, gamma-ray bursts can strip away atmospheres from nearby planets or disrupt existing ecosystems on any nearby celestial bodies. The intense radiation can break molecular bonds, leading to chemical alterations in the affected areas and potentially affecting the development of life. Essentially, the aftermath of a gamma-ray burst can create a landscape that is radically different from what existed prior. Over the long term, the impact of gamma-ray bursts can reverberate throughout the cosmos. They can enrich the interstellar medium with heavy elements formed during the birth and death of massive stars, contributing to the overall chemical evolution of galaxies. In this way, gamma-ray bursts serve not only as incredible cosmic events, but also as important catalysts for both destruction and creation within the vast tapestry of the universe. Gamma-ray bursts, immense explosions that occur in distant galaxies, release more energy in a few seconds than our sun will emit throughout its entire lifetime. When these bursts happen in our cosmic neighborhood, they can significantly affect planets and any potential life forms. Imagine a gamma-ray burst as a violent flash of light and energy. If one were to occur close enough to Earth, the powerful radiation could strip away the ozone layer, which acts as our protective shield against harmful ultraviolet light from the sun. Without this vital layer, life on land would face serious challenges, exposing ecosystems to radiation that can damage genetic material, disrupt cellular processes, and ultimately threaten survival. These bursts also unleash high-energy particles that travel through space at nearly the speed of light. If these particles collide with a planet's atmosphere, they can create secondary radiation effects that reach the surface, possibly leading to mass extinctions. For planets like Earth, which have life, these events are potentially catastrophic. If such a burst were directed towards a planet with developing life, it might cause a rapid extinction event, disrupting evolutionary pathways before they can fully unfold. On a broader scale, the frequency of gamma-ray bursts in an area of the universe could influence where life might thrive. Regions with frequent gamma-ray activity could be less conducive to the development of life due to their destructive potential. This makes the search for habitable exoplanets an even more intricate task, as astronomers must consider not just the distance from a star and the presence of water, but also the nature of cosmic events like gamma-ray bursts that might impact these worlds. While gamma-ray bursts are fascinating astronomical phenomena, their potential impact on planets and the possibility of life can be profound and devastating, marking them as areas of concern for scientists studying the cosmos and the fate of life within it. Cosmic voids are vast, empty regions of space that contain very few galaxies compared to the surrounding areas. They are essentially the opposite of galaxy clusters, which are densely packed with stars and celestial bodies. To define a cosmic void, scientists look for areas where the density of matter, particularly galaxies, is significantly lower than average. These regions can span millions of light-years across and often appear as large, dark gaps in the fabric of the universe. Recognizing cosmic voids involves analyzing large-scale surveys of galaxies. Researchers map the distribution of these galaxies across the universe and identify areas that are sparsely populated. Advanced statistical techniques help to quantify these gaps in density. When scientists notice a region that is noticeably empty, surrounded by more concentrated clusters of galaxies, that's a strong indicator of a void. Because of their size and emptiness, cosmic voids also have interesting implications for our understanding of the universe's structure and evolution. They help illuminate how matter is distributed on a cosmic scale, providing insights into the forces that shaped the cosmos since the Big Bang. Understanding voids can reveal information about dark energy and dark matter, which play crucial roles in cosmic expansion and structure formation. Thus, cosmic voids are not just empty spaces, they are integral to unraveling the mysteries of the universe and our place within it. The universe is composed of various forms of matter, with baryonic matter being the kind that makes up stars, planets, and even our own bodies. In an attempt to understand the composition of the cosmos, scientists have come across a puzzling observation. There seems to be a significant amount of baryonic mass that is simply unaccounted for. This is commonly referred to as the missing baryonic mass. One of the primary clues comes from cosmic measurements. Observations of the cosmic microwave background radiation, which is a faint glow left over from the Big Bang, suggest that baryonic matter should exist in quantities that are not fully visible or detectable with our current instruments. Essentially, if all the baryonic matter assumed to exist were accounted for, we would expect to see more visible matter in galaxies and clusters than we do. One hypothesis surrounding this missing mass is that much of it may be in forms that are elusive to us. For instance, baryonic matter can exist as cold, diffuse gas that is incredibly thinly spread across vast regions of space, possibly in cosmic filaments between galaxies. This means it lacks the density necessary to shine or reflect light, making it difficult for telescopes to detect. Additionally, some scientists speculate that parts of this missing baryonic matter could be hidden in the atmospheres of exoplanets or in small, faint stellar objects that do not emit enough light to be noticed. Another intriguing theory involves primordial black holes, which would have formed in the early universe and could account for some of the unaccounted mass. This mystery is not merely an academic pursuit, it holds significant implications for our understanding of galaxy formation, the evolution of the universe, and the fundamental laws of physics. As new observational techniques are developed and our technology advances, we inch closer to unlocking the secrets of the missing baryonic mass, hoping to piece together not just the structure of the cosmos, but also the very fabric of reality itself. Cosmic voids are vast, empty regions of space that play a crucial role in shaping the universe's large-scale structure. Picture a honeycomb, where the dense parts represent galaxies and clusters of galaxies, while the empty spaces between them illustrate these cosmic voids. These vast vacuums can have a profound influence on the behavior of cosmic matter. As matter in the universe is attracted to areas of higher density due to gravitational forces, cosmic voids create a unique dynamic. They act almost like gravitational traps, where the surrounding denser regions draw matter away from the voids, causing them to become even emptier. This effect means that the voids can expand over time as galaxies move towards denser clusters. The presence of these voids also influences the movement of galaxies. Objects on the outskirts of a void may experience different gravitational influences compared to those deep within a galaxy cluster. Moreover, the existence of cosmic voids affects the cosmic web, the large-scale structure of the universe characterized by filaments and clusters made of galaxies and dark matter. The voids create gaps that define this web, allowing researchers to study the patterns of galaxy formation and growth. Over billions of years, these interactions and movements lead to the rich tapestry of structure we observe today, with galaxies, clusters, and voids representing the universe's complex evolutionary history. Cosmic voids are not just empty spaces, they are integral components that influence the distribution of matter, the dynamics of galaxies, and the overall architecture of the universe. Their presence helps scientists understand the expansion of the universe and the proliferation of cosmic structures, serving as indicators of the universe's evolution since the beginning of time. Voids, those vast and empty regions in the universe with very few galaxies, tell us a profound story about the distribution of dark matter and dark energy. When we observe the cosmos, we find that galaxies are not evenly scattered. Instead, they are organized in a web-like structure, with dense areas known as filaments and large empty spaces known as voids. These voids are the places where normal matter is rare, but they reveal critical insights into what we cannot see. The existence of voids suggests a significant amount of dark matter lurking in the universe's outskirts. While these voids appear nearly empty, they have a lower density of regular matter compared to their surroundings. However, dark matter, which interacts through gravity but not with light, is believed to be more prevalent in these regions than initially perceived. The gravitational influence of dark matter helps to shape the cosmic web, pulling galaxies toward these filaments, while leaving the voids relatively unoccupied. In terms of dark energy, these voids also hold clues about the universe's expansion. Dark energy is thought to be the driving force behind the acceleration of the universe's expansion. In areas of low density, like voids, the effects of dark energy become more pronounced. This enables scientists to observe how cosmic structures evolve over time and to understand the influence of dark energy in shaping the large-scale structure of the universe. By studying the characteristics of voids and their surrounding structures, researchers can better comprehend the interplay between dark matter, which contributes to the cosmic web's formation, and dark energy, which influences the expansion rate of the universe. Together, these elements highlight the complexities of cosmic architecture and help to reveal the mysterious forces that govern the universe. Thus, voids serve as essential markers in our quest to unravel the enigmatic properties of dark matter and dark energy, leading to a deeper understanding of our universe's history and destiny. Voids, the vast empty spaces between galaxies, play a significant role in enhancing our understanding of the universe's expansion. Imagine the universe as a sponge filled with clusters of matter resembling granules. The area between these clusters is where voids exist, regions of relatively low density with few galaxies. Researchers examine these voids to uncover insights about the expansion rate of the universe. As the universe expands, galaxies move away from each other, and this movement is more pronounced in denser regions. In contrast, voids expand differently. They essentially stretch and become less dense over time. By studying the distribution and evolution of these voids, scientists can gather evidence on how the expansion is accelerating. This acceleration suggests the influence of mysterious forces in the universe, such as dark energy, which seems to drive galaxies apart. Moreover, voids provide a unique backdrop against which the effects of cosmic expansion can be observed. Their relatively empty nature allows astronomers to measure the positions and movements of galaxies more accurately, revealing how they respond to the expanding universe. Understanding these dynamics is essential not only to address questions about the fate of the cosmos, but also to refine models of the universe's structure and growth. Voids offer a clear window into the broader cosmic dance, showcasing how the universe continues to unfold, revealing its mysteries in the vastness of space. The cosmic microwave background, often referred to as the CMB, serves as a crucial snapshot of the early universe, providing an invaluable window into its infancy. Imagine a time when the universe was hot, dense, and filled with a glowing fog. As it expanded, this fog cooled, allowing protons and electrons to combine and form hydrogen atoms. This moment, known as recombination, occurred around 380,000 years after the Big Bang, leading to the release of photons, particles of light that could finally travel freely through space. The CMB is the remnant glow of that ancient time, now stretched and cooled to a temperature just above absolute zero. Observing this background radiation is akin to peering back in time, as it carries information about the conditions present at the universe's beginning. By studying its delicate temperature variations, scientists can glean insights about the density and distribution of matter in the early cosmos. These tiny fluctuations in temperature reflect gravitational effects from the clumping of matter, revealing the seeds of the galaxies that would eventually form. Essentially, the CMB maps out the baby picture of the cosmos, showing us where matter was slightly denser due to gravitational pulls and where it was less so. This information has become a cornerstone for understanding the universe's evolution, the formation of large-scale structures, and even the rate of its expansion. As we decode these patterns, we gain a deeper appreciation of how the universe transformed from a hot, chaotic explosion into the vast, structured expanse we observe today. The cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, provides a snapshot of the early universe, offering scientists a wealth of information about its origins and evolution. However, within this ancient light lies a series of anomalies, irregularities that provoke intrigue and challenge our understanding of cosmic history. These anomalies are slight fluctuations in temperature and density detected across the sky. They suggest that the universe is not perfectly uniform, but contains variations that hint at its formative moments. For instance, some areas of the cosmic microwave background appear to be unusually smooth, while others exhibit unexpected clumpiness, which raises questions about the processes that led to galaxy formation and the large-scale structure of the universe. One particularly puzzling anomaly is known as the cold spot, a region that is less dense and cooler than surrounding areas. The nature of this cold spot leads scientists to speculate about potential origins, such as evidence of large cosmic structures that reshaped the fabric of the universe, or even the possibility of interactions with other universes. These are theories that, while captivating, venture into the realm of speculation because current understanding does not fully account for such phenomena. Moreover, these anomalies challenge the prevalent model of cosmology, which posits that the universe is dominated by dark energy and dark matter. If the cosmic microwave background contains unexpected features, it implies that our grasp of these fundamental elements may need re-evaluation. Thus, each anomaly is not merely an inconsistency, it is a doorway to deeper inquiries about the nature of our universe. As researchers explore these mysterious signals, they find themselves unraveling ever more complex threads of cosmology, ultimately constructing a more comprehensive picture of the cosmos. This journey continues to captivate scientists and laypersons alike, as they seek answers to questions that may redefine humanity's understanding of everything from the universe's infancy to its ultimate fate. The cosmic microwave background, often abbreviated as CMB, is a faint glow of radiation that fills the universe and serves as a remnant from the early moments after the Big Bang. This radiation carries vital information about the state of the universe at that time, providing a snapshot of the cosmos roughly 380,000 years after its inception. The fluctuations in the CMB are not just noise, they reveal significant details about the universe's structure and history. These fluctuations represent slight variations in temperature across the surface of the CMB. Imagine ripples on a pond. These temperature differences indicate areas of slightly higher and lower density in the early universe. When the universe expanded and cooled, regions with a higher density had more matter, which later became the stars, galaxies, and clusters we observe today. Conversely, areas of lower density would eventually form voids. By analyzing these fluctuations, scientists can learn about the universe's composition, including the proportions of ordinary matter, and dark energy. Moreover, they provide insight into fundamental cosmological phenomena, such as inflation, an extremely rapid expansion of space in the universe's earliest moments. Fluctuations also produce a unique signature concerning the geometry of the universe, helping astronomers determine whether it is open, flat, or closed. The cosmic microwave background's fluctuations are like a cosmic fingerprint, containing a wealth of information that tells us about the universe's birth, evolution, and the underlying fabric of spacetime itself. By studying these patterns, researchers peel back layers of cosmic history, revealing the story of the universe from its earliest days to the present. The cosmic microwave background, often referred to as the CMB, provides a snapshot of the universe when it was just about 300,000 years old. This precious remnant radiation, cooling and barely detectable, fills the entire cosmos and carries vital clues about the early conditions of the universe. When scientists first started studying the CMB in detail, they discovered unexpected features that posed challenges to existing cosmological models. One of the striking aspects of the CMB is its remarkable uniformity, with slight variations known as anisotropies that reveal the seeds of all present structures in the universe. However, certain patterns and the overall temperature fluctuations do not perfectly conform to predictions made by the traditional inflationary model of the universe. Inflation posits that a rapid expansion occurred in the first moments after the Big Bang, yet these discrepancies suggest that our understanding of inflation itself may need refinement or revision. Moreover, the distribution of these anisotropies offers insights into the density of matter and energy in the universe. Current models struggle with aligning the observed amount of cosmic structure with the levels of dark matter and dark energy that are presumed to exist. For instance, the magnitude of cold spots in the CMB suggests that we may be missing components in our equations that could explain how everything interacts on a grand scale. Additionally, recent discoveries about the universe's rate of expansion, known as the Hubble constant, present a paradox when measured using CMB data versus local observations. These findings raise intriguing questions about the fundamental principles of cosmology and highlight the need for a deeper understanding of how the universe evolved from its early state into what we observe today. While the CMB offers a wealth of information and is a cornerstone of our understanding of cosmology, its revelations also simultaneously challenge and stimulate revisions to the existing models. It's a constant reminder that the universe is far more complex than we might initially presume, and that scientific inquiry is an ever-evolving journey into the unknown. The cosmic microwave background, often referred to as the afterglow of the Big Bang, represents a crucial remnant from the early universe. Imagine the universe as an enormous balloon that began to expand rapidly, filling with energy and particles shortly after the Big Bang occurred. In those initial moments, the universe was extremely hot and dense, filled with light and radiation. As time passed, this expanding universe began to cool. Eventually, about 300,000 years after the Big Bang, it cooled enough for electrons and protons to combine and form hydrogen atoms. With this formation, light could finally travel freely without constantly scattering off charged particles. This moment is known as recombination and marks the point when the universe became transparent to radiation. What we now observe as the cosmic microwave background is the relic radiation, essentially the glow of that baby universe, now stretched and cooled due to the ongoing expansion of the cosmos. Today, instead of the intense heat found right after the Big Bang, we detect this ancient light as a faint, uniform microwave radiation that permeates the entire universe. It's as if we are hearing a distant echo of the universe's nascent moments, capturing a snapshot of its infancy. This afterglow holds vital clues about the universe's origins, composition, and evolution, helping scientists piece together the events that occurred in those formative times. At the edge of a black hole, scientists have observed incredibly mysterious forces at play, primarily linked to the phenomenon of gravity and the effects of extreme space-time curvature. This region, known as the event horizon, acts as a boundary beyond which nothing can escape the black hole's influence, not even light. As objects approach this boundary, they experience an intense gravitational pull that is fundamentally different from anything experienced on Earth or even within our solar system. One of the key aspects of the forces observed near black holes is gravitational tidal forces. Imagine being on a roller coaster as it approaches a steep drop. Just as the thrill is mixed with the fear of falling, objects nearing a black hole begin to stretch and compress due to differing gravitational forces acting on them. This can lead to what scientists term spaghettification, where an object is elongated and ultimately torn apart as it gets closer to the event horizon. Moreover, the immense gravitational field influences light itself, bending its path in a phenomenon known as gravitational lensing. This means that we can sometimes observe objects behind a black hole due to the way light curves around it, creating a distorted view of the cosmos. Additionally, black holes are often surrounded by an accretion disk, a swirling mass of gas and particles that spirals inward at high speeds. The interaction of this material, heated to extreme temperatures, can emit powerful radiation and create jets that shoot out into space along the black hole's rotational axis. These jets are some of the most energetic phenomena in the universe and provide insight into the complex forces at work around black holes. The forces observed at the edge of black holes reveal the extremes of gravitational physics, challenging our understanding of the universe and prompting further exploration into the nature of space-time itself. Each discovery brings us closer to unraveling the true mysteries of these cosmic giants. The event horizon of a black hole presents an intriguing scientific puzzle because it acts as a boundary beyond which information cannot escape. Imagine it as a one-way street. Once you pass through it, return is impossible. This raises fundamental questions about the nature of reality and the very fabric of our understanding of physics. At the event horizon, the gravitational pull of the black hole becomes so immense that even light, a fundamental carrier of information, cannot break free. This leads to a paradox. If no information can escape from inside this boundary, what happens to the matter that crosses it? What about the information contained in that matter? Theories such as the conservation of information suggest that this information must somehow be preserved, even as it seems lost to us. This conflict between the laws of quantum mechanics, which emphasize preservation of information, and general relativity's treatment of black holes, fuels a scientific debate. Physicists are challenged to reconcile these two fields, leading to innovative ideas like the concept of black hole evaporation. This suggests that black holes could eventually lose their mass and emit radiation, possibly releasing the information they had swallowed. The event horizon thus stands at the intersection of our understanding of physics, forcing scientists to grapple with profound questions about the universe, the limits of knowledge, and the nature of existence itself. It exemplifies just how much there is yet to uncover in the realm of black holes and the fundamental principles that govern our cosmos. The idea of escaping from a black hole's gravity is one of the most profound mysteries in astrophysics. Once an object crosses the event horizon, it enters a region where escape seems impossible, defined by the overwhelming strength of gravity. Understanding this phenomenon begins with the nature of black holes themselves, which are formed from the collapse of massive stars. Their gravitational pull is so intense that nothing, not even light, can escape once it has crossed that critical boundary. However, theories suggest intriguing possibilities. Some scientists speculate about the existence of quantum tunneling, a strange principle where particles might pass through barriers they typically cannot overcome. This concept is abstract and relies on the peculiarities of quantum mechanics, hinting that under certain conditions, particles could escape the pull of a black hole in ways that we barely understand. Furthermore, there are ideas rooted in theoretical physics, like the existence of wormholes, hypothetical passages that could connect distant regions of space and time. If such structures could exist, they might offer a route for information or even matter to circumvent the black hole's event horizon, allowing them to escape what seems like an inescapable fate. It's essential to note that these theories remain speculative. Observations of black holes have shown us their power and their behavior, but they have yet to provide concrete evidence of any mechanisms that allow escape. The nature of black holes challenges our understanding of physics, combining gravity, quantum mechanics, and the very fabric of spacetime into an enigmatic puzzle. As research advances, we inch closer to unraveling these mysteries, possibly revealing whether escape from their grasp is ever truly feasible. The jets emitted by black holes are captivating phenomena that spark the curiosity of scientists and the public alike. These jets, which are streams of charged particles moving at astonishing speeds, shoot out from the regions surrounding black holes, particularly from their accretion disks. An accretion disk is a swirling mass of gas and dust that gathers around a black hole. As material spirals in, gravitational forces and extreme energy levels cause some of it to be ejected instead of being consumed. What makes these jets intriguing is their immense power and reach. They can extend far beyond the host galaxy, traveling across vast distances in space. This journey is facilitated by the black hole's intense magnetic fields, which play a crucial role in channeling and accelerating particles away from the black hole's vicinity. Imagine a high-speed water hose. In this case, the jets act like an ultra-fast stream, shooting particles and energy across the cosmos. Moreover, these jets can have significant effects on their surroundings. As they plow through intergalactic space, they can influence star formation and help to shape the structure of galaxies. Their interactions with the surrounding medium are not just destructive, they can also lead to the birth of new stars as shockwaves compress gas and dust. Scientists continuously explore these phenomena to unravel the mysteries of black holes and their jets. Understanding them holds keys to fundamental questions about the universe, including the dynamics of galaxy evolution and the nature of gravity itself. This blend of extreme physics and the potential for new discoveries keeps black holes and their jets at the forefront of astronomical research. Just beyond a black hole, particularly beyond its event horizon, lies a realm filled with speculation and mystery. Scientists hypothesize that this region may host various forms of matter and energy that challenge our conventional understanding of physics. One key concept is the idea of exotic matter, which differs from the familiar substances we interact with daily. Exotic matter is theorized to possess unusual properties, such as negative energy density, allowing for peculiar behaviors that could influence the surrounding environment of a black hole. Another fascinating aspect involves the strong gravitational forces at play. As matter spirals into a black hole, it forms an accretion disk made up of hot gas and dust. This material can reach incredibly high temperatures and emit energy in the form of radiation, particularly X-rays. This radiation acts as a beacon that provides insights into the black hole's presence and the dynamics occurring around it. Additionally, the intense gravitational field near a black hole can lead to the generation of gravitational waves. These ripples in the fabric of space-time carry energy across the universe. As black holes merge or interact, they can create waves that scientists can detect even from vast distances, linking them to the existence of energy forms previously unobserved. Some researchers also delve into the realm of vacuum energy, a concept rooted in quantum field theory. This idea suggests that even in seemingly empty space, fluctuations in energy could create temporary particles. Near a black hole, these quantum events may interact with the gravitational field, potentially leading to unique phenomena such as Hawking radiation. This theoretical effect proposes that black holes can emit radiation due to quantum mechanical effects near their event horizons, subtly bridging the gap between the known and the unknown. Just outside a black hole, scientists speculate about exotic matter with unconventional properties, radiant emissions from accreting matter, gravitational waves, and vacuum energy fluctuations. Each of these areas represents a frontier of exploration, inviting us to rethink the nature of matter and energy at the extremes of the universe. The Hubble tension refers to an ongoing debate in the scientific community about the expansion rate of the universe, known as the Hubble constant. Astronomers use this constant to measure how fast galaxies are moving apart from each other, an observation central to our understanding of cosmic expansion. The tension arises because two different methods of calculating this expansion rate yield conflicting results. On one hand, astronomers measure the Hubble constant by observing nearby celestial objects, particularly Cepheid variable stars and supernovae. This approach gives them a direct measurement of distances and speeds, resulting in a higher value for the expansion rate. On the other hand, estimates based on observations of the cosmic microwave background, the relic radiation from the Big Bang, provide a significantly lower value. This latter method relies on models that describe the universe's early conditions and how it evolved over time, leading to different interpretations of the expansion process. The discrepancy between these two approaches is what we call the Hubble tension. This disagreement is crucial because it challenges our understanding of fundamental cosmological principles, which include the makeup and behavior of the universe's components, such as dark energy and dark matter. If we cannot reconcile the two values, it raises the possibility that our current models, based on assumptions about cosmic consistency, may need adjustments or even a complete overhaul. Scientists are now re-evaluating the foundational constants that describe the universe. They are investigating possibilities like the potential existence of new physics or previously unaccounted forces influencing cosmic expansion. Ultimately, the Hubble tension pushes researchers to reconsider what we know about the universe's past, present, and future, potentially reshaping our understanding of its overall structure and dynamics. The expansion of the universe is a profound topic that intrigues astronomers and physicists alike. Scientists measure this expansion rate using various methods, which can lead to different results. One primary approach involves observing distant galaxies and measuring how quickly they are moving away from us. This movement is consequentially linked to the expansion of space itself. However, when researchers apply different techniques, such as examining the cosmic microwave background radiation or utilizing supernovae as standard candles for distance measurements, they often encounter discrepancies. These differences are not just minor variations, they highlight a challenging puzzle. For instance, one method may suggest that the universe is expanding at a certain rate, while another may indicate that the rate is significantly different, leading to uncertainty about fundamental aspects of cosmology. These inconsistencies provoke new mysteries about the universe's composition and evolution. They raise questions. Is our understanding of dark energy, the mysterious force driving the acceleration of expansion, incomplete? Could there be new physics at play that we have yet to uncover? These hypotheses spur exciting new fields of study, encouraging scientists to delve deeper into the nature of the universe, potentially altering our comprehension of time, space, and the very fabric of reality itself. As researchers attempt to resolve these discrepancies, they embark on an exploration that could unveil hidden truths about the universe's origins and fate, forcing us to reconsider everything we believed we knew about cosmic evolution. Each mystery uncovered not only enriches our understanding, but also opens the door to even more profound questions, compelling us to reach for insights that challenge the limits of our knowledge. The Hubble tension refers to the disagreement between two methods of measuring the universe's expansion rate, often described as how quickly galaxies are moving away from each other. On one side, observations of the cosmic microwave background radiation, which is a remnant from the early universe, suggest a certain rate of expansion. On the other side, measurements taken from nearby supernovae and the distance to galaxies show a significantly higher rate. This discrepancy raises important questions not just about the measurements themselves, but about our understanding of fundamental cosmic components, including dark energy. Dark energy is the mysterious force thought to be driving the accelerated expansion of the universe. If the two methods of measuring cosmic expansion yield different results, it hints that the underlying physics of dark energy may not be fully understood. Perhaps dark energy behaves differently than current models predict, or there could be additional factors or unknown entities at play. This uncertainty casts a shadow over our predictions about the fate of the universe. If the higher Hubble constant is correct, the implications for the universe's future could be profound. With an accelerated expansion, galaxies might drift further apart at an ever-increasing rate, suggesting a lonely future where galaxies lose sight of one another. This scenario, known as the Big Freeze, leads to a universe increasingly empty and cold over trillions of years. Conversely, if the lower rate is accurate, it might suggest a different scenario for the future, possibly leading toward a slower rate of expansion that could, in the far distant future, allow for some gravitational influences and interactions among cosmic structures. Ultimately, the Hubble tension doesn't just challenge our measurement techniques, but also forces us to reconsider the very nature of the universe we inhabit, urging scientists to explore new theories and possibly redefine what we think we know about dark energy and cosmic evolution. As researchers continue to investigate, the implications of these findings may drastically alter our understanding of the cosmos and its ultimate destiny. The Hubble constant is a crucial figure in cosmology, as it defines the rate at which the universe is expanding. Measuring this constant, however, has turned into a significant scientific debate because different methods yield different results. One primary approach involves observing distant galaxies and their light, specifically using the relationship between the brightness of standard candles, like certain types of exploding stars known as supernovae, and their distance from Earth. This method indicates a faster expansion rate of the universe. Conversely, another technique uses measurements of the cosmic microwave background radiation, which is the afterglow of the Big Bang. This method suggests a slower expansion rate. The discrepancy between these two methods raises profound questions. If one measurement is correct, what does that imply about our understanding of the universe's composition and its history? It suggests that there might be unknown factors or phenomena affecting our measurements, possibly hinting at new physics beyond our current theories. This discord is not merely academic, it challenges our fundamental perceptions of the universe and its evolution. Researchers are currently engaged in intensive discussions, collecting data and refining techniques in hopes of reconciling these differences, or at the very least, understanding the reasons behind them. Ultimately, how we measure the Hubble constant impacts our grasp of cosmic history and the fate of the universe itself, making this scientific debate both critical and captivating. The Hubble tension refers to a significant difference in the measurements of the expansion rate of the universe, as indicated by two different methods. One method uses observations of the cosmic microwave background, the relic radiation from the early universe, while the other relies on observing nearby galaxies. Resolving this discrepancy is crucial because it affects our understanding of fundamental cosmic concepts, such as the age and size of the universe. If the expansion rate is confirmed to be higher when observing galaxies, it suggests that our models of cosmic history might be missing important aspects or phenomena. It could lead us to rethink the role of dark energy, which is believed to be driving the accelerated expansion of the universe. Alternatively, if the lower rate is validated, it might raise questions about the physics governing the early universe or suggest unknown particles and forces that influence cosmic evolution. Understanding the true nature of the Hubble tension could reshape our knowledge about the evolution of cosmic structures and the ultimate fate of the universe. It's not merely a technical challenge, it's a key to unlocking the universe's history, guiding scientists in their pursuit to comprehend the intricate tapestry of events that have unfolded since the Big Bang. Resolving this tension is vital for piecing together the grand story of our cosmos. Gravitational waves are ripples in the fabric of space-time, created by some of the most violent and energetic events in the universe. Imagine dropping a stone into a still pond. Ripples spread outward from the point of impact. Similarly, when massive objects like black holes or neutron stars collide or orbit each other, they create disturbances in space-time. This disturbance travels outward at the speed of light, stretching and compressing space itself as it goes. These waves were first predicted by Albert Einstein a century ago as a consequence of his theory of general relativity, which describes how gravity operates on cosmic scales. However, detecting them has been a monumental challenge. They are incredibly faint by the time they reach Earth, often smaller than the width of a human hair. The technology required to measure them involves sophisticated equipment that can detect these minute changes with extreme precision. Gravitational waves remain a mystery in astrophysics because they offer a new way of observing the universe. For decades, astronomers relied on light and other electromagnetic signals to learn about distant celestial events. However, gravitational waves reveal information that light cannot, providing insights into the detailed dynamics of massive objects and the nature of extreme environments. Events like the merging of two black holes, which might not emit significant light, become accessible to study through gravitational waves. Moreover, studying these waves can help us understand fundamental questions about the universe, such as its expansion and the nature of dark matter and dark energy. They challenge existing theories and prompt new inquiries into the fundamental workings of physics. As researchers continue to explore this new realm of astrophysics, gravitational waves hold the promise of radically transforming our comprehension of the cosmos and the forces that shape it. Gravitational waves represent a groundbreaking way to observe the universe, much like how the invention of the telescope allowed astronomers to see distant stars and galaxies. Imagine ripples spreading across a calm pond after a stone is tossed in. These waves travel through space-time itself, generated by some of the most violent and energetic events in the cosmos, such as merging black holes or exploding stars. What makes gravitational waves exciting is that they carry unique information about their origins that light cannot provide. While telescopes observe light in various wavelengths, which can be obscured by dust and gas, gravitational waves travel unimpeded through the universe. This means they give us a clearer picture of events that occurred billions of years ago, allowing us to understand phenomena that were previously invisible to our eyes. The detection of these waves began with advanced instruments capable of measuring minuscule changes in distance caused by passing waves, changes that are smaller than the size of a proton. When these waves are detected, they reveal their source. The merger of supermassive objects creates a cosmic signal that scientists can analyze to learn more about the behavior of matter and energy under extreme conditions. This new frontier opened the door to a different field of astronomy known as multi-messenger astronomy, where information from gravitational waves is combined with traditional observations of electromagnetic signals, such as visible light, radio waves, and X-rays. By studying cosmic events through both light and gravitational waves, researchers can paint a more complete picture of how the universe operates. Thus, gravitational waves offer an innovative tool for exploring the cosmos, unlocking secrets of phenomena that shaped the universe and challenging our understanding of fundamental physics. With ongoing developments in technology and precision measurement, they promise to guide our journey into the depths of space-time, revealing the dramatic stories written in the fabric of the universe itself. The detection of gravitational waves has opened a thrilling new chapter in our understanding of the universe. These ripples in spacetime, first confirmed in 2015, provide astonishing insights into astronomical events that were once hidden from view. When massive objects like black holes or neutron stars collide, they release colossal amounts of energy that send gravitational waves traveling across the cosmos. This allows scientists to observe phenomena that light cannot reach, unveiling moments of cataclysmic cosmic events in real time. Through various observed events, such as the merger of black holes, we have confirmed predictions made by Albert Einstein's theory of general relativity. Each detection acts like a cosmic fingerprint, allowing us to measure the masses and spins of the merging bodies. This has led to a better understanding of how these massive objects form and evolve over time, offering clues about the very nature of black holes, including their origins and frequencies of collisions. These observations have also enhanced our understanding of neutron stars, particularly through events where such stars collide. Such collisions not only produce gravitational waves, but also lead to the creation of heavy elements, contributing to our knowledge about the origins of elements in the universe. By studying the light emitted from these events, in conjunction with gravitational wave data, astronomers can piece together more comprehensive stories of stellar evolution and element formation. Furthermore, these discoveries hint at a more intricate tapestry of the universe, suggesting that gravitational waves might provide a new method for exploring unseen phenomena, such as the mysteries of dark matter and dark energy. The implications extend even further into cosmology, enabling us to probe the fabric of the universe in ways previously unimagined, including shedding light on the early moments of cosmic history right after the Big Bang. The detection of gravitational waves is not just a remarkable technical achievement. It represents a revolutionary way for humanity to explore the universe, transforming our understanding of cosmic events and fundamentally changing our perspective on how we perceive the vastness of space and time. Gravitational waves represent a groundbreaking revelation in our understanding of space-time. At their core, these waves are ripples caused by the acceleration of massive objects, such as merging black holes or neutron stars. To visualize this, picture dropping a stone into a still pond. The water surface responds with ripples that expand outward from the point of impact. Similarly, when immense bodies in the universe accelerate, they create disturbances that travel through the fabric of spacetime itself. Traditionally, our perception of gravity was primarily influenced by the concept established by Isaac Newton, where gravity acted at a distance without any medium. Einstein's theory of general relativity revolutionized this perspective by portraying gravity as a curvature in the space-time continuum caused by mass. Gravitational waves offer a practical demonstration of this theory in action. When these waves pass through the universe, they stretch and compress the distances between objects, creating minute changes in their positions. This phenomenon challenges scientists to rethink the very nature of how gravity operates across vast distances, suggesting it not only influences objects on contact, but can also affect them at incredible ranges without direct interaction. Moreover, the detection of these gravitational waves has opened an entirely new avenue in astrophysics, allowing scientists to observe events that were previously invisible using traditional telescopes. This newfound ability to listen to the universe through gravitational waves is similar to hearing thunder when lightning strikes, a clear signal of a powerful cosmic event. With each new detection, our comprehension of the life cycles of celestial objects expands, pushing the boundaries of how we understand the universe's fabric itself. Through these incredible advancements, gravitational waves are not merely a discovery, they represent a fundamental shift in the way we perceive and interact with space-time. They challenge established theories and inspire new questions about the mysterious phenomena of the cosmos, provoking curiosity about what other secrets a deeper exploration might reveal. The discovery of gravitational waves marks a pivotal moment in our understanding of the universe, particularly relating to the theories of relativity and quantum mechanics. At its core, gravitational waves are ripples in the fabric of space-time, created by the acceleration of massive objects, such as two colliding black holes. This phenomenon, predicted by Albert Einstein's theory of general relativity over a century ago, confirms that gravity can influence the structure of space-time itself. When these waves were first detected, It not only validated key elements of general relativity, but also opened up new avenues for investigation. Scientists can now observe cosmic events in ways they never could before, transforming our capabilities in astrophysics. For instance, they can study the aftermath of these collisions and gain insights into the properties of black holes and neutron stars, enhancing our understanding of the fundamental laws that govern the cosmos. However, the interaction between gravitational waves and quantum mechanics introduces fascinating questions. General relativity describes the grand scale of the universe, while quantum mechanics governs the behavior of particles at the tiniest scales. These two frameworks usually operate independently, yet the study of gravitational waves could reveal how they intersect, potentially leading to a unified theory that encapsulates both realms. Exploring this relationship has implications for phenomena such as the nature of black hole singularities, points where gravitational forces are thought to become infinite and existing physics breaks down. By examining gravitational waves, scientists hope to uncover clues about how quantum effects might operate in extreme gravitational fields, challenging our understanding of reality and the fundamental forces of nature. In this continuously evolving narrative, the discoveries around gravitational waves not only affirm the robustness of relativity, but also invite deeper exploration into how we might reconcile the seemingly disparate worlds of gravity and quantum mechanics. Each detection is not merely an observation, it is a stepping stone toward unraveling the complex tapestry of the universe that we are only beginning to understand. Exoplanets, or planets outside our solar system, intrigue scientists for several reasons. First and foremost, they expand our understanding of planetary systems. For centuries, we believed our solar system was a unique phenomenon, but the discovery of exoplanets has revealed a diverse array of worlds, some of which challenge our preconceived notions about how planets form and evolve. These distant planets come in various sizes, compositions, and orbits, and some exist in the habitable zone of their stars, regions where conditions may be just right for liquid water to exist. This finding fuels the search for extraterrestrial life. The curiosity about whether we are alone in the universe drives a significant amount of research as scientists seek to identify biosignatures or signs of life on these distant worlds. Technological advancements have made it possible to investigate exoplanets in detail. Instruments designed to detect tiny dips in starlight allow us to identify these planets and infer their properties, such as atmosphere composition and temperature. The possibility of finding Earth-like planets that could potentially harbor life makes the study of exoplanets not just a pursuit of knowledge, but also a quest for understanding our own existence in the cosmic landscape. Moreover, the study of exoplanets sheds light on the history and future of our solar system. By comparing other planetary systems' formation and evolution with our own, we can build a more comprehensive picture of how planetary bodies come to be. The exploration of exoplanets opens a new realm of scientific inquiry, challenging us to rethink what we know about the universe and our place within it. Detecting exoplanets, especially those with unconventional characteristics, is a fascinating endeavor that combines advanced technology with creative techniques. Scientists often use methods that allow them to infer the presence of these distant worlds without directly observing them, as they are often too faint against the brightness of their host stars. One of the primary techniques is called the transit method. This involves monitoring the brightness of a star over time. When a planet crosses in front of its star from our viewpoint, it temporarily blocks a tiny fraction of the star's light, causing a periodic dimming. This method can reveal not just the existence of a planet, but also its size and orbit. For unconventional exoplanets, such as those that may have unusual sizes or orbits, the pattern of dimming can provide key insights into their characteristics. Another method utilized is radial velocity, which examines the wobble of a star caused by the gravitational tug of an orbiting planet. As the planet moves, it causes the star to shift slightly toward and away from us, which can be detected as changes in the star's light spectrum. This technique reveals not only the presence of the planet, but also its mass, offering clues to its density and composition, which can be particularly useful for identifying planets with surprising features. In cases where both methods might fail, scientists turn to gravitational microlensing, where the gravity of a massive object, like a star or an exoplanet, bends and focuses the light from a more distant background star. This technique can detect planets that are much farther away from their parent stars or that exist in environments where traditional methods might struggle. It allows researchers to uncover planets that might otherwise remain hidden due to their unconventional locations or characteristics. As our technology continues to advance, space-based telescopes and sophisticated data analysis methods are also enhancing our ability to detect and study these extraordinary worlds. By collaborating and sharing findings across various scientific fields and institutions, scientists are building a more comprehensive picture of the diversity and complexity of exoplanets, with unique attributes, capturing imagination and curiosity along the way. Each discovery contributes to our understanding of the universe and the remarkable variety of planetary systems it holds. Rogue planets are a fascinating enigma in our understanding of the cosmos. Unlike the planets that orbit stars, rogue planets drift freely through the galaxy, untethered to any solar system. This solitary existence raises intriguing questions about their origins and characteristics. One mystery is how these planets come to be. Scientists suggest that they might be the remnants of planetary systems that were disrupted, possibly due to gravitational interactions with larger celestial bodies. This could lead to planets being ejected from their birthplace, sending them out into the vastness of space, where they wander for billions of years. Alternatively, some may form in isolation, outside any star's gravitational influence, from the same material that creates other celestial bodies. Understanding their formation could reveal much about the dynamics of planetary systems and the conditions necessary for planet birth. Another captivating aspect of rogue planets is their potential to harbor life. While most planets are heated and illuminated by their stars, rogue planets might maintain warmth through their internal processes or even due to residual heat from their formation. This raises the possibility that they could possess subsurface oceans or other environments where life might flourish, albeit in conditions dramatically different from those on Earth. Thus, the search for life now extends beyond the familiar solar orbits, delving into the shadowy reaches of space. Additionally, the sheer number of rogue planets is an open question. Studies suggest that they could outnumber the stars in our galaxy, but quantifying them is challenging. Finding these elusive worlds depends on the technology and methods available to astronomers, who often rely on indirect detection techniques since rogue planets do not emit their own light. Researchers continue to develop new tools to identify these solitary wanderers and learn more about their physical properties and atmospheres. Lastly, the dynamics of how rogue planets interact with other celestial bodies presents yet another layer of complexity. As they traverse the galaxy, they can affect the orbits of stars, disrupt planetary systems, and potentially play a role in galaxy evolution. Each encounter could lead to new formations or disrupt existing ones, highlighting the interconnectedness of cosmic phenomena. The mysteries of rogue planets invite us to explore further, revealing the diversity of our universe and challenging our understanding of planetary systems. Through continued research, we may uncover the secrets of these celestial nomads and their roles in the vast tapestry of the galaxy. The atmosphere of an exoplanet can serve as a fascinating detective with unseen clues about its origin and evolution. When we examine the atmospheric conditions of these distant worlds, scientists gather valuable information that paints a picture of how they came to be. Consider the elements found in a planet's atmosphere. Gases like carbon dioxide, methane, and water vapor all tell a story. For example, a rich presence of methane might suggest biological processes if it occurs alongside oxygen in significant quantities, hinting at possible life. However, if methane appears in isolation or with other gaseous elements, it could indicate a completely different chemical process at work, such as geological activity. Temperature and pressure play critical roles too. A planet that orbits close to its star may have intense heating, which can cause extreme weather patterns. Conversely, worlds that are cooler may harbor more water and stability. By studying these conditions, scientists infer whether a planet can hold on to an atmosphere in the long term or if it has lost it due to various processes, such as impacts or solar winds. The presence of clouds or storms can also reveal past changes. These might indicate a history of seasonal shifts or climatic changes over eons. An atmosphere that has shifted from a thick greenhouse-rich environment to a thinner one may signify cataclysmic events like asteroid impacts or significant volcanic activities. The atmospheric fingerprints of an exoplanet unveil their past journeys through space and time. By analyzing these conditions, scientists piece together not only the story of individual planets, but also deepen our understanding of how different environments form and evolve throughout the universe. Planetary systems are as varied as the stars they orbit, and many have revealed peculiarities that challenge our existing models of formation and dynamics. One of the most surprising discoveries is the prevalence of gas giants situated very close to their parent stars. Traditionally, we believed that such massive planets would form at greater distances, where cooler temperatures allow gas to condense. However, many large exoplanets have been observed in extremely tight orbits, leading scientists to re-evaluate their models of planetary migration, which suggests these giants may move inward from their original formation zones over time. Another fascinating anomaly comes from the discovery of planets that exist in orbits that are highly inclined or tilted compared to their stars' rotational axes. This misalignment can hint at past gravitational interactions, possibly involving other large bodies that have since been ejected or destroyed. Such scenarios suggest a more chaotic early solar system environment than previously imagined. Moreover, some planetary systems feature unusual configurations, such as multiple planets sharing similar orbits or exhibiting resonances with one another. These arrangements challenge our understanding of stability and suggest that the processes of formation and interaction can lead to configurations that were once thought to be unlikely. Additionally, the presence of super-Earths, rocky planets that are larger than Earth but smaller than gas giants, pushes the boundaries of our current models. Their abundance raises questions about the conditions of their formation and the materials available in their protoplanetary disks. All these peculiarities highlight the complexity of planetary system evolution and indicate that our existing models may not fully account for the dynamic processes at play in the cosmos. As we continue to gather data from telescopes and missions, it is clear that each new discovery has the potential to reshape our understanding of how planets form and interact across the universe. Time can feel quite different depending on the cosmic scale being considered, from the minute movements within an atom to the vast expanse of the universe. At the smallest scale, time operates within the realm of subatomic particles, where interactions occur at incredibly brief intervals. Here, time can almost seem irrelevant, as particles flicker in and out of existence in fractions of a moment, making it difficult to capture events in a way that relates to our experience of time. As we move to larger scales, such as planets and stars, time becomes more familiar. The cycles of day and night define time on Earth, creating predictable patterns governed by the planet's rotation. Meanwhile, celestial bodies like stars live for millions or even billions of years, with their life cycles marked by processes that unfold over timescales so vast that human comprehension struggles to grasp them. This introduces the idea that time is not a constant in the cosmos. It stretches and compresses based on the context of what is being measured. At the grandest scale, the universe itself operates on a timeline that spans the birth of stars, the merging of galaxies, and the eventual fate of cosmic structures. The concept of cosmic time suggests a timeline that doesn't align neatly with our everyday experiences. For instance, as astronomical objects move closer to regions with strong gravitational fields, time can slow down significantly relative to observers in less powerful fields. This was famously illustrated through the phenomenon of gravitational time dilation, where time literally ticks slower for an object in a strong gravitational field compared to one further away. The differences in how time is perceived across these scales remind us that our experience of time is intricately tied to the fabric of space and the forces governing the universe. What might feel like a constant or a simple progression on Earth cannot be easily applied to the grand expanse of the cosmos, where events unfold in their own unique rhythms and narratives across different layers of reality, at tremendous speeds in a spaceship. To the observer on the spaceship, time passes normally. However, to the observer on Earth, the clock on the spaceship seems to tick slower. This effect reveals that as an object approaches the speed of light, time for that object slows down relative to an outside observer. Additionally, gravity plays an astonishing role in time dilation. Higher gravitational fields, like those near a massive planet or a black hole, can cause time to pass more slowly compared to areas with weaker gravity. It's as if gravity itself is a sort of timekeeper. Wherever gravity is stronger, time crawls at a slower pace. This phenomenon is not merely academic, it has practical implications, affecting everything from the technology we use, like GPS satellites, to our understanding of cosmic events. The most captivating aspect of time dilation lies in its implications for human experience. If two identical twins were separated, with one aging on Earth and the other traveling close to the speed of light in space, they would reunite with one twin significantly younger than the other. This concept raises profound questions about the nature of reality and the fabric of our universe. It invites us to ponder what time truly is, challenging the notion that it universally flows at the same rate for everyone, everywhere. Such mysteries drive scientists to explore deeper into the universe, searching for answers that could illuminate our understanding of time, space, and existence itself. Time dilation unveils some of the most intriguing mysteries of the universe, fundamentally reshaping our understanding of time itself. At its core, time dilation is a consequence of Albert Einstein's theory of relativity, which suggests that time is not a constant, but rather a variable that can stretch and compress based on speed and gravity. Imagine two observers, one standing still on Earth, and another traveling time loops and paradoxes are fascinating concepts often explored in theoretical physics and cosmology. Imagine time as a river flowing in one direction. In most scenarios, events move in a straight line, much like droplets cascading downstream. However, the idea of a time loop suggests that certain sections of this river might curve back on themselves, allowing an event to potentially repeat. One prominent model discussed in relation to time loops is the concept of closed time-like curves. These curves allow for paths through space-time that can lead you back to an earlier point in time. Picture walking in a circle on a flat surface. If time were structured similarly, you could eventually find yourself revisiting past moments. This notion raises intriguing questions about causality, the principle that cause precedes effect. If you were to travel back in time, your very presence could alter past events, creating what is known as a paradox. One well-known thought experiment involves the classic grandfather paradox. If someone were to travel back and inadvertently prevent their grandfather from meeting their grandmother, it raises the question, how could they have existed in the first place to make such a trip? This illustrates the potential contradictions intrinsic to time travel, leading some theorists to propose multiple timelines or parallel universes as resolutions. Each decision or alteration could create a new branch in the fabric of reality, ensuring that the timeline continues forward while sidestepping impossible contradictions. Theoretical physicists often explore the implications of these constructs using advanced equations and models, including those involving black holes, quantum mechanics, and the very architecture of the universe itself. Although still in the realm of speculation, these ideas capture our imagination and challenge our understanding of time itself, suggesting that the universe may harbor mysteries far beyond our current comprehension. Time is a fundamental aspect of the universe, shaping how events unfold from the Big Bang to the potential end of everything. From our perspective, time moves forward, creating a sequence of past, present, and future. In cosmology, this linear progression has implications for the universe's evolution and ultimate fate. As the universe expands, galaxies move away from each other, a phenomenon that has been observed over many years. This expansion influences what happens to celestial bodies over time. If the rate of this expansion continues to accelerate, the universe could approach a state known as heat death. In this scenario, stars would eventually burn out, leaving behind a cold, dark cosmos where matter is so spread out that no significant interactions could occur. Conversely, if the expansion slows down and reverses, it could lead to a big crunch. Imagine time reversing itself, drawing everything back together until the universe collapses into an infinitely dense point. This cyclical notion suggests an ongoing narrative through time where beginnings and endings might not be as definitive as they seem. In another possibility, time could stretch indefinitely as the universe expands forever, leading to a gradual fading of everything, including the fabric of space itself. This scenario creates an eternity of vast emptiness, where any remaining matter drifts apart and energy dissipates. Ultimately, time serves as the thread that weaves through the universe's narrative. It shapes how we understand our existence and the fate of everything around us, framing our ideas about origins, transformations, and endings in the grand cosmic theater. No matter how the universe evolves, time continues to be the canvas upon which the story of existence unfolds. The arrow of time is a concept that helps us understand how time seems to flow in a particular direction, from the past through the present and into the future. This idea is central to our experience of the world, but it presents a significant puzzle for scientists. Unlike space, which we can move through in all directions, the directional flow of time is seemingly one way, raising essential questions. At the heart of this mystery lies the second law of thermodynamics, which states that in an isolated system, disorder tends to increase over time. Think of a glass of ice melting in a warm room. Initially, the system is organized with ice and cold water, but as time flows forward, the ice melts and the heat spreads out, increasing disorder. This transition from order to disorder defines our perception of time moving forward. Yet, when we examine the laws of physics, they do not inherently dictate a preference for one direction over another. The equations that govern the fundamental forces are symmetrical. They treat both time directions equally. This leads to a paradox. If the laws of nature do not distinguish between past and future, why does time still seem to have a defined direction? Another layer of complexity arises from the role of consciousness in observing time. Our memories form a narrative that is inherently tied to our past experiences, reinforcing the idea that time has a clear flow. When we make observations, we create records that shape our understanding of events. This raises the question of whether our perception of time as an ever-advancing entity is simply a feature of human experience rather than a fundamental property of the universe. Special and general relativity add further dimensions to this discussion. They illustrate that time can be influenced by speed and gravity, leading to scenarios where time for one observer proceeds differently than for another. This flexibility complicates the notion of a universal arrow of time, making it reliant on relative circumstances. The arrow of time continues to be a central mystery in physics because it intertwines fundamental principles of thermodynamics, consciousness, and the intricacies of spacetime. Understanding why we experience time as flowing in one direction and how this relates to the underlying laws of the universe remains one of the most fascinating inquiries that scientists continue to explore. Supermassive black holes, often found at the centers of galaxies, play a crucial role in shaping their dynamics and evolution. Imagine these colossal entities as immense gravitational engines that exert significant force on their surroundings. They can be billions of times more massive than our Sun, and this immense mass pulls in surrounding gas, dust, stars, and even entire solar systems. As material approaches a supermassive black hole, it forms an accretion disk around it, where particles accelerate and heat up, emitting radiation across various wavelengths. This process not only contributes energy and momentum back into the galaxy, but also influences star formation rates. In some cases, the energy generated can create powerful jets that shoot out at nearly the speed of light, pushing gas away from the black hole. This ejection of material can suppress star formation in certain areas of the galaxy, creating a complex interplay between the black hole and its environment. The gravitational influence of the black hole also helps to regulate the orbits of stars and gas within the galaxy, acting almost like a cosmic glue. By stabilizing the galaxy's core, the black hole can determine how stars move in its vicinity, leading to distinctive orbital patterns that can be observed. Additionally, there's an important relationship between a supermassive black hole's mass and the overall mass of its host galaxy. As galaxies grow, their central black holes may grow too, but not in isolation. They often dictate the conditions that promote or hinder galaxy growth. Some researchers believe that this connection influences whether galaxies become spirals or ellipticals over cosmic time. Through these mechanisms, supermassive black holes are not merely passive remnants of the past, but actively shape the fate of their host galaxies, contributing to the vast tapestry of structures we observe in the universe. The rapid formation of supermassive black holes in the early universe is a fascinating enigma that has captured the attention of astronomers and physicists alike. These colossal entities, with masses millions to billions of times that of our own Sun, seem to have emerged surprisingly quickly, just a few 100 million years after the Big Bang. This timeline raises intriguing questions about how something so massive could form in such a short period. One of the primary mysteries lies in understanding the process of their formation. Conventional theories suggest that black holes begin as stellar remnants, formed from the gravitational collapse of massive stars. However, this pathway takes a considerable amount of time. In the early universe, where the density of matter was much higher, some researchers propose that supermassive black holes might have formed from massive clouds of gas collapsing rapidly under their own gravity, bypassing the typical star formation stages. This scenario aligns with models of extreme cosmic conditions that existed shortly after the Big Bang. Another perplexing aspect is the extreme growth rate required for these black holes to achieve their immense sizes in a brief span. For a black hole to grow into a supermassive type, it must consume a significant amount of surrounding material, and the availability of this material in such an early universe is uncertain. Quasars, which are bright, energetic objects powered by accreting supermassive black holes, have been observed at staggering distances, indicating that they existed when the universe was still young. To sustain their brightness and support the growth of their associated black holes, there must have been abundant gas and dust available, raising questions about the environmental conditions during that epoch. Additionally, there are theories proposing that smaller black holes could merge, leading to the formation of larger ones, or that rapid gas inflows might feed existing black holes at incredible rates. The dynamics of how these black holes interacted with their host galaxies and the surrounding environment plays a vital role in their development. Understanding these processes hinges on deciphering the intricate balance between gravitational forces and the pressures from surrounding cosmic materials such as radiation and gas. Astrophysicists are leveraging advanced technologies, such as powerful telescopes and simulations, to unravel this cosmic riddle. Observations of the universe's oldest galaxies and the analysis of their structure provide key insights into the attributes of the environments in which these supermassive black holes formed. Still, mysteries remain, urging scientists to continue exploring the interplay of cosmic factors that contributed to the emergence and evolution of supermassive black holes in the early universe. Supermassive black holes are not just the most extreme objects in the universe, they play a crucial role in the cosmic ecosystem, particularly in their interaction with dark matter. Dark matter, which remains elusive and undetectable by conventional means, constitutes a significant portion of the universe's total mass. Unlike normal matter, which interacts electromagnetically and can emit light, dark matter primarily influences its environment through gravity. In the vicinity of a supermassive black hole, which is located at the centers of most galaxies, the effects of dark matter can be profound. The gravitational pull of the black hole and the surrounding dense clusters of dark matter alters the movement of stars, gas, and other matter within a galaxy. Essentially, dark matter contributes to the total gravitational well that a supermassive black hole resides in, making it easier for incoming matter to be captured and consumed by the black hole. Furthermore, as galaxies evolve and merge, dark matter halos, which are massive regions filled with dark matter, can collide and interact with each other. This interaction can funnel additional gas and dust into the black hole, providing it with more fuel to grow. Observations suggest that supermassive black holes could influence the distribution of dark matter through their gravitational forces, potentially leading to the release of energy that might affect the large-scale structure of the universe. While supermassive black holes can continue to draw matter toward themselves, they coexist with dark matter in a complex gravitational dance, one that shapes galaxies and the fabric of space itself. Together, they serve as a balancing act of forces, helping us unravel the mysterious interplay of visible and invisible matter in our universe. The growth of supermassive black holes is a captivating area of research in astrophysics, with various theories attempting to explain how these colossal entities formed and evolved in the centers of galaxies. One prominent theory centers on the idea that supermassive black holes originate from the merging of smaller black holes. These smaller counterparts could be remnants of massive stars that went supernova. As they collide and combine over time, they can grow significantly, feeding on surrounding matter and gravitationally attracting new gas and stars. Another intriguing perspective suggests that supermassive black holes could have formed directly from vast clouds of gas in the early universe. In this scenario, conditions in these dense gas clouds allowed them to collapse under their own gravity, leading to the creation of a black hole at their core. This direct collapse model posits that these primordial black holes could evolve into the supermassive giants we observe today, particularly in the environments of young and active galaxies where gas was plentiful. Additionally, some researchers focus on the role of rapid accretion, where a black hole consumes gas and star material at remarkably high rates. This can lead to an explosive period of growth, generating immense energy and radiation, making these black holes difficult to observe in their formative stages. The balance of inflow and outflow of material due to energetic feedback from forming stars and active galactic nuclei can heavily influence this growth. Moreover, there are theories that intertwine these ideas, suggesting that supermassive black holes could form through a combination of mergers, direct gas collapse, and efficient accretion processes, adapting dynamically as galaxies evolve. This interplay of mechanisms illustrates the complexity and diversity of scenarios in which supermassive black holes can develop, highlighting an ongoing quest to unravel the mysteries of the universe's most enigmatic objects. Each theory opens up new avenues for exploration, driving further discovery as we strive to understand not just supermassive black holes, but the galaxies that host them. Supermassive black holes, those titanic entities lurking at the centers of galaxies, play an intricate role in shaping the vast structures of the universe. Their connection to cosmic structures is intertwined with their gravitational influence and the energy they exert. Imagine the universe as a vast tapestry, where galaxies are the stitching holding it together. Supermassive black holes act like anchors in this fabric, holding entire galaxy clusters in place. As matter falls into these black holes, it doesn't just vanish. It generates immense energy, often seen as powerful jets and winds. These can influence star formation within their host galaxy, either promoting it by compressing gas and dust or hindering it by blowing those materials away. Such interactions can ripple through the cosmos, affecting neighboring galaxies and even larger cosmic structures. Moreover, observations have revealed that the mass of a supermassive black hole tends to be linked to the characteristics of its host galaxy, including the rate at which stars are formed and the galaxy's overall size. This relationship suggests that black holes and galaxies co-evolve, each shaping the other over cosmic time. On an even grander scale, supermassive black holes sit at the heart of galaxy clusters, which are the largest gravitationally bound structures in the universe. Their collective gravitational pull helps to form the cosmic web, where galaxies are interconnected through a vast network of dark matter. This web exhibits a sponge-like structure, and supermassive black holes contribute to its construction by influencing how matter is distributed throughout. Supermassive black holes are more than isolated phenomena. They are key players in the evolutionary drama of the universe, sculpting cosmic structures from the smallest scales of individual galaxies to the immense architecture of galaxy clusters. At the boundary of the observable universe, we encounter a vast expanse shrouded in uncertainty and intrigue. This boundary represents the farthest distance from which we can detect light emitted after the Big Bang, which took place billions of years ago. Beyond this limit lies an area we cannot see, leading to numerous questions about what could exist there. One of the primary mysteries is related to the uniformity of the universe. Despite the apparent chaos and variety we observe, the cosmic microwave background radiation reveals that the early universe was extraordinarily homogeneous. How did these uniform conditions lead to the intricate structures we see today, such as galaxies and clusters of galaxies? This raises the question of whether there might be regions outside our observable bubble with entirely different properties, which could hold clues about the nature of the universe itself. Another captivating aspect is the potential existence of other universes. The concept of the multiverse suggests that our universe might be just one of many, each with its own set of physical laws and constants. If this idea holds true, then what lies beyond the observable universe could be an entirely different realm, untouched by the forces that govern our experience. Then there's the enigmatic dark matter and dark energy, which together make up much of the universe's mass-energy content, but remain poorly understood. The boundaries of the observable universe enhance our curiosity regarding their role. Could these phenomena vary beyond what we can observe, affecting cosmic evolution in ways we haven't yet imagined? Finally, the accelerating expansion of the universe leaves us pondering its fate. Questions arise about what lies at the edge of this expansion. As galaxies move away from us and light from distant stars becomes increasingly redshifted, will they eventually disappear from view? This raises fundamental questions about the ultimate destiny of the universe and whether life could exist in vastly distant future epochs where stars become scarce. Thus, the boundary of the observable universe is not just a limit, it is a profound threshold of knowledge and imagination, beckoning us to explore the unknown mysteries that lie beyond our current grasp. Each discovery that edges closer to this boundary may change our understanding of the cosmos in ways we are only beginning to fathom. The limits of what we can see in the cosmos are defined by several factors, primarily the nature of light, the expanding universe, and the technology we use to observe the heavens. When we look into space, we are essentially looking back in time. Light from distant celestial objects takes years to reach us, and thus, the further away we look, the earlier in the universe's history we are observing. Our ability to see depends on the distance light has traveled. The observable universe is often described as a bubble surrounding Earth, stretching out to the farthest points from which light has had time to reach us since the beginning of the universe, often referred to as the Big Bang. This bubble encompasses galaxies and cosmic phenomena that are billions of years old. The edge of this observable universe represents a sphere beyond which light has not yet reached us. Anything beyond that remains invisible. However, the universe is not static. The expansion of space itself means that as galaxies move away from us, their light becomes redshifted, stretching to longer wavelengths and possibly leaving them beyond the limits of our current detecting capabilities. This expansion can make it seem like less light is available to observe. Our observational tools also limit what we can see. Telescopes, for example, have specific capabilities, determining the faintest and most distant objects we can identify. The development of advanced technology, including radio telescopes and space-based observatories, has significantly expanded our view. Each new generation of instruments enhances our understanding, allowing us to capture light across different wavelengths, from radio waves to gamma rays, piecing together an ever-expanding picture of the universe. The limits of our cosmic sight are set by the speed of light, the ever-expanding breadth of space, and the evolving technology that helps us peer deeper into the vast universe, continually pushing the boundaries of our knowledge and curiosity. Just beyond our current observational capabilities lies a fascinating realm filled with potential phenomena that could reshape our understanding of the universe. One prominent example is dark matter, an invisible substance that makes up a significant portion of the cosmos. While it does not emit light or energy, its existence is inferred from the gravitational effects it has on galaxies and cosmic structures. Imagine trying to see a hidden object by observing how it influences the movement of nearby objects. That's how we detect dark matter. Another intriguing phenomenon is dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. This force remains elusive, as we cannot directly measure it, but it plays a crucial role in the universe's fate. Think of the expansion as a balloon inflating. Dark energy is the unseen air pushing it outward, influencing how galaxies move apart over time. Beyond these constituents, the possibility of more exotic objects like primordial black holes, which could have formed in the very early universe, tantalizingly lurks on the edges of our detection abilities. These black holes might be of various sizes, and their effects could offer clues to the conditions of the early cosmos. Moreover, there could be entire regions in space where the laws of physics as we know them do not apply as expected, leading to phenomena that are difficult to predict or understand. As we develop more advanced technologies and methodologies, these enigmatic aspects of the universe are likely to be revealed, offering new insights and potentially rewriting the cosmic narrative. Each discovery opens a window into a reality that might challenge our fundamental beliefs about space, time, and existence itself. The cosmic horizon fundamentally changes our perspective on infinity by framing it within the limits of what we can observe. Imagine standing on a vast beach, gazing out at the ocean. The horizon you see is a boundary. If you were to venture further beyond that point, you could discover more, but only to a degree. In the vastness of the universe, the cosmic horizon represents a similar boundary, a limit to how far we can see due to the finite speed of light. As the universe expands, light from the farthest reaches takes time to reach us. The cosmic horizon delineates the edge of our observable universe, beyond which light has not yet had the chance to travel to us since the beginning of time. It implies that there are countless galaxies and cosmic phenomena we cannot access or perceive. Thus, while infinity suggests boundless space, our understanding is constrained by this horizon, creating a paradox. The universe may be infinitely large, yet we can only comprehend a finite portion of it. This concept also leads to intriguing questions. Are there regions beyond our horizon filled with galaxies, or is it possible that the universe contains structures we can't even fathom? The implication of a cosmic horizon invites us to consider that while the universe itself could be infinite, our experience and observations are inherently limited. We are faced with the dilemma of infinity. There exists an expanse of the cosmos, possibly with endless complexity, but our knowledge is forever bound by the limits of our observational reach, reminding us that the universe is both vast and mysterious. Delving into the edge of the observable universe opens a fascinating window into the fundamental workings of our cosmos. This boundary represents the farthest light that has had the time to reach us since the universe became transparent, about 15 billion years ago. What lies beyond this edge is still veiled in mystery, but any discoveries made as we push further could significantly reshape our understanding of the universe. If we were to uncover structures or patterns that challenge current theories, it could lead to a paradigm shift in cosmology. For example, finding evidence of previously unknown forms of matter or energy could prompt scientists to revise the current models of the universe's composition. This could mean a shift away from our reliance on dark matter and dark energy, concepts that were established to explain phenomena that couldn't be seen directly. Moreover, exploring this edge could provide insights into the expansion of the universe itself. If researchers discovered that the rate of expansion is not consistent, it may lead to new theories about the forces at play in the cosmos and perhaps hint at new physics altogether. Additionally, identifying anomalies in the cosmic microwave background, essentially the afterglow of the Big Bang, could illuminate the conditions of the early universe, revising our timeline of cosmic events. Every new piece of data can influence theories of gravity, fundamental forces, and the very fabric of space and time. As scientists gather information from advanced telescopes and cutting-edge technology, each discovery at the universe's edge has the potential to introduce new questions, refine existing theories, and inspire fresh lines of inquiry that keep the quest for knowledge vibrant and ongoing. The journey toward understanding the universe is as exciting as it is impactful, and what we find could forever alter humanity's perspective on existence itself.